or is there, let's see.
I would like to skip ahead since sometimes the slides are small and I have permission. Want to shift? Should I? I just want to shift. Yeah, just go. I tend to oh, yeah.
Yes, sir. Uh, okay. Everyone, I'm Supreet Singh Baga. I am associate at Department of Mechanical Engineering at IIT Delhi. All throughout the day, I'll talk about microchip electrophoresis and various aspects of microchip electrophoresis, various types of electrophoresis techniques, and how we can simulate these techniques on computer so that we can design the electrophoresis assays in advance before we go into the laboratory and do the actual experiment. So the first lecture is on microchip electrophoresis. So just a quick introduction of microfluidics. So essentially, microfluidics is you can say plumbing in a way on a small scale. So what I have in my hand is a microfluidic device. This is made in glass and it has a network of microchannels. So for example, this is how a typical microfluidic device looks like. There are channels made in this device and the device is bonded, so the only access to these channels is at the ends through these wells or reservoirs. So what we can do is that we can connect this microfluidic device to the external world through these reservoirs. So essentially what we have is a piping network on a very small scale. Typically the channel size is channel width is of the order of 100 micrometers. That's smaller than your hair diameter, or you can say of the order of your diameter of your hair strand, and we can also go to smaller dimensions of 10 micrometers, and we can make these microfluidic devices in various substrates, and that I will talk about towards the end of the day today. And one of the applications of microfluidic devices is to develop point of care medical diagnostic devices. So the advantage you'll see, and there are certainly a lot of advantages in miniaturizing electrophoresis systems, and that's how the initial interest in microfluidics started, and thereafter people found additional applications of microfluidics. But the main advantages for us in terms of microchip electrophoresis is that we can significantly reduce the reagent use. Now we have microchannels whose length is of the order of few centimeters, the width, the diameters, the height are of order of 10 to 100 micrometers. So the volumes that we are talking about are 1 microliter or even in nanoliters. So that's the amount of liquid that we need, and what we can do is that we can develop portable instruments where this can go as a cartridge and you can do your sample testing on field rather than bringing the samples to the lab. So this field holds a lot of promise, and microchip electrophoresis is one of the significant successes of the microfluidic technology, which has seen commercialization and it's already in the market, this technology. So what I'll do in today's lecture is to talk about microchip electrophoresis, or those who are familiar with analytical chemistry techniques, how we can integrate capillary zone electrophoresis onto a microfluidic device, and what are the advantages, why we want to actually reduce the size of a device, and how we can get benefit of that. So before that, we need to understand what goes on when we apply an electric field through an electrolyte solution that fills a capillary. So for example, I have typically electrophoresis. This microfluidic device is made of glass. Okay, and here what I'm considering is, let's just consider a glass capillary or a glass microchannel, and we fill this glass microchannel with an aqueous electrolyte solution. So now the surface of glass is actually acidic because of silanol groups. So you have SiOH groups over here, and in contact with water, glass is actually pretty strong acid in that way. So it will donate a proton and the surface will acquire negative charges. And that is what happens when you fill your a glass of water. Still you have this negative charge on the surface, but what happens is that on large scales the bulk forces are important, the surface effects are not important. As we miniaturize the size of our device, the surface effects start becoming prominent. So what we have now here is, we have negative charges which are immobile on the glass surface, and electrolyte has positive and negative charges both, right? So let's say we have sodium chloride solution, or you have some buffer solution. So what will happen is that negative charges are going to preferentially attract positive charges, okay, and there is also diffusion of charges, okay, diffusion of mobile ions in the electrolyte. But the net result is that you have immobile charges on the surface, but you will have net positive charges near the surface of the capillary. Okay. So what we get is, at equilibrium, a diffuse layer of ions, positive ions near the surface, then negative ions, because we have to maintain net electroneutrality. This this layer where you have more is really small, you can't see it, okay, but the effects of this are what you can observe. So this layer we call as electric double layer, and typically its thickness is of order of 10 nanometers. So certainly we can't see it through a microscope, let's say, at such small dimensions. So what we can think of it is that we have dimensions of 10 micrometers or more of the channel, and 3 orders of magnitude smaller dimensions we have for the electric. So what you can think is that near the surface you have excess positive charges which can also move. So this happens when you fill your micro with the electrolyte solution. We haven't applied any electric field, and this formation you can think of taking place almost instantly. Okay. Now what we do is that through this capillary or microchannel, we are going to apply an electric field and see what happens. So what you can do is, you can do electrodes at the ends in the vessels of the capillary that are connecting the capillary, and here I have applied positive voltage and this is negative voltage, so the electric field is pointing towards the left. Now there are two things that happen, two transport processes, distinct transport processes take place upon application of this actual electric field. So first is that these charges near the channel, these charges, okay, under the effect of the electric field, they start moving and they drag the fluid along. So what you get is, you get a fluid flow just by applying electric field through this channel, and there is no pumping. Okay. So what you get is, you can think that the walls of the channels are moving and you get a plug shaped velocity profile. So you can flow liquids just by applying electric fields, there is no need for a pump, okay, and that is the motion of fluid flow, and the velocity at the walls, okay, we can think that the flow is slipping, and this slip velocity is proportional to the electric field. The proportionality constant is called electroosmotic mobility. So typically what we do is that we apply an electric field of order 10 kilovolts per meter. That means you have um, let's say a 1 centimeter long microchannel, then you just have to apply 100 volts to get very high voltage, high electric field of 10 kilovolts per meter. Another effect is electromigration. You have ions in the bulk solution. The ions in the bulk solution are also going to migrate under the effect of electric field. So the positive ions in the bulk solution are going to move towards the negative ions, and the negative ions are going to move towards the positive electrode. This phenomena is called electrophoresis or electromigration, and the velocity of the ions for small ions typically is also proportional to electric field, and the proportionality constant is called electrophoretic mobility. So typically, if you apply a field of 10 kilovolts per meter, the ion velocity and even the electroosmotic velocity is of this order, about 0.3 millimeters per second. Okay. So that's the speed that we are talking about. This is the order of magnitude of electric field that we are talking about. So now what is electrophoresis? So different ions and ionic species, they have different mobility, and that can be because of various reasons. Some ions are big, some ions have less charge. Large molecules like DNA, they have different mechanism of having differential mobility. If you put a gel or if you put a polymer, these DNA strands will get entangled with these polymers, so their mobility will become dependent upon the size. Proteins will have different mobility depending upon the pH of the solution, the isoelectric point. So for weak acids, weak bases, you can vary the pH and the mobility will change. So effectively, mobility depends upon how much charge you have and what is the mass of the molecule. Now, microchip electrophoresis deals with how we can separate species or analytes from a mixture based on their differential electrophoretic mobility. So two ions, let's say calcium and magnesium in a solution, let's say a milk sample you want to separate, then we can do so because calcium and magnesium will have different mobility. So that, and how to separate them and how to detect them is what we do in capillary electrophoresis. So before we go, let me just point out the main difference between electroosmotic flow and the typical flow that we have by pumping. So if you think that consider that this is a channel and you apply a pressure gradient, you apply high pressure over here and low pressure over here, for example when we use pumps to flow, then what happens is that here I'm showing an experiment where the fluorescent band of a fluorescent dye was initially introduced at the channel inlet, and now you have applied pressure you have applied pressure drop, and now you have pressure driven flow. So when the flow occurs, fluid flow occurs under pressure, then you get a parabolic velocity profile. So you have zero velocity near the walls and the maximum velocity at the channel center, and this is a parabolic shape velocity profile. So the dye at the center is going to move, but dye at the channel ends, the walls, is not going to move. So what you will have is, you will have distortion of this zone over time, but that doesn't happen with electroosmotic. It appears, okay, the walls are not moving, but because the ions are moving, it appears that the flow is plug shaped and the flow is slipping at the walls, and you have a band that just propagates or just advects as a band. And in this case, the dye is neutral dye. There is no electrophoresis. This is just due to the flow. But in practice, what we have is that when you apply electric field through a microchannel, you will have both electromigration of ions and also osmotic flow. So both these motions will be superimposed, and we are going to use both of them for our advantage. So now we come to microchip electrophoresis. And essentially the principle of microchip electrophoresis is same as what we do in regular electrophoresis, in capillary zone electrophoresis, in gel electrophoresis the medium is different, but otherwise the process is similar. So what I'll focus on is how to integrate this on a microfluidic device rather than talking about the electrophoretic process, the capillary zone electrophoresis technique in more detail. So, but let's just recap what is microchip electrophoresis or capillary zone electrophoresis. So, what we do is that consider a single capillary, okay, and this is just a schematic. In later, we'll use a network of microchannels, but think that there's a capillary in which you fill a background electrolyte solution. Background electrolyte is, let's say, a sodium acetate buffer, for example. Okay, it's a buffer solution with relatively high conductivity and it maintains the pH of the solution. Okay. And this is important. The conductivity of the solution is governed by the background electrolyte. Now, at the inlet, you introduce your sample whose components you are going to, or whose constituents, the ionic constituents are what we want to separate and detect. So, in my picture over here, I just have two types of ions, okay, two types of analytes, S1 and S2. And of course, and these are not two ions, these are, I mean, you have large number of ions of two species. And I'm plotting concentration versus the axial location. So, somehow we want to generate an initial condition where you have a background electrolyte and you have your sample at the inlet of the capillary, and the most important thing is that the sample concentration, the analyte concentration, should be significantly lower than the background electrolyte concentration. The reason is that, and it will be clear even further, that the presence of these sample ions, because these have their own charge mobility, they should not affect the conductivity of the bulk solution. Otherwise, you have some nonlinear effects. So now what we do is that we apply voltage. So what's going to happen? These ions are going to move under the effect of electric field. Okay, but all of them are not going to move at the same speed. They have different mobility. Okay, S1, if we say, has higher mobility. So positive ions will have positive mobility, negative ions will have negative mobility, but I am talking about the when I say mobility is higher and lower, I am just talking about the absolute values. So S1 has higher mobility, so the zone of sample S1 races ahead, whereas S2 remains behind. Okay, but that's not the only phenomena that is taking place. As you can see in the pictures in this cartoon, what we have is that while these zones propagate, you also have molecular diffusion. You can't control diffusion. So these zones become broader and broader, and the peak concentration decreases over time. So what we do is that we can put a detector over here. As these zones migrate over the detector, you will record some signal, and you can analyze what was the composition of the mixture, provided these samples have different mobility from each other. Okay, so this phenomena has been is widely used, okay, in analysis of DNAs, RNAs, proteins, small ions for environmental monitoring. You can imagine, you know, there are so many applications for this, and the peaks or the analytes are identified by the location of the peaks and how much time the analyte has taken from the beginning to reach the detector. That is how you detect. Okay, so this is my a very quick introduction to microchip electrophoresis. But the question is how we can create this condition where on a tiny microfluidic device like this, where you have a sharp initial band and then you can do this separation. So the way to do it is on a microfluidic device is that this cross-shaped microfluidic network. So you have these microfluidic channels where at the ends you have these reservoirs, and just focus on this. We'll come back to this later on. So what we do is that we fill the channel network with the background electrolyte, okay, and then we put the sample that we want to analyze in one of the reservoirs. I'll call this as the north reservoir. This is north, this is south, east and west. So if you put the sample in the north reservoir, then what we can do is we can dip the electrodes at the end of the the capillaries or the channels, and this is also dipped somehow. There's some issue, this line has shifted, but imagine that this electrode is also dipped. Okay. Now what we can do is, actually this is a resistor network. Okay, it's just a network of resistors, so I can vary the voltages at the ends. I can control the voltage at the junction. So what I do is that in the initial step, I control the voltages at the ends in a way that the electric field is pointing in this direction. Okay, the junction, the potential at the junction is smaller than the potential over here. It's smaller than this, but it is larger than the voltage applied at the southwest. So what we have is that electric field is pointing in the direction shown in these arrows, and it's going to derive electroosmotic flow. You are also going to have electrophoresis, but in this system, let's say that you have very high electroosmotic flow than electrophoretic velocity. So the sample ions are going to fill the vertical channel. Then what we do is we switch the voltages at the channel ends in a way that the electric field starts pointing from here, from left to the right. Okay, so we do this. So the initial band, it disintegrates into multiple zones which we detect. Okay, and the electric field in this in the vertical channels is such that no additional sample enters from these reservoirs. Okay, we switch the field in a way that we can pinch a sample from the junction. We can just take a pinch of that sample and then it separates into different zones. So here is a video of this process. Let's okay, so you'll see a video of this process. So first what we will see is, in this particular case for visualization, there are two analytes and those are tagged with fluorophores. So you see this injection step, that is the first step I was showing over here. Okay, and the next step will be the separation step. There's some issue, let's see. Okay, so in this particular case, the channels have a dimension of order 100 micrometers. So this is the injection step, and now you can switch the voltage, and you will see that the sample has split up into two zones which keep on migrating, but they also diffuse over time. Okay, so this is the basic process of microchip electrophoresis. So our goal is that we want to have as good separation as possible, and what you can do on a microfluidic chip is that you can, here I'm showing only 2 peaks, but you can actually separate a very large number of peaks. This is taken from a paper where they use microchip electrophoresis for DNA sequencing on a microfluidic device, and this is one of the major successes of microfluidic technologies, and it's widely commercialized. If you look at a bioanalyzer equipment in your laboratories or in some medical setting, it is actually using microchip electrophoresis, and this is the kind of cartridge that goes into that device. So the interest in microfluidics initially started just because there was interest in miniaturizing the electrophoresis, microchip electrophoresis system. So now what our goal is that uh, throughout this remaining part of this lecture is that how we can improve our separation. Okay, how we can get better and better separations through the devices that we have, what kind of parameters we can choose to get better separation. But first we need to define how we say that a particular experiment or particular electrophoresis separation is better than the other. So we need to define some metrics. So one is sensitivity, other is resolution. So consider an experiment, okay? So where you have a detector over here which records fluorescence, and let's say we are just talking about analytes which are fluorescent. So these analytes, they move over the detector and you record the fluorescence versus time. So this is my electropherogram, okay? So this peak corresponds to a species that has higher mobility because it is reaching the detector in shorter amount of time, smaller time. Okay. So now we can define sensitivity. So how low concentration I can detect. So as I said, the concentrations will decrease over time because your band is diffusing. So if you have initially high concentration, the signal that you get, the peak signal that you get while when the zone reaches the detector is going to be proportional to the initial concentration. So how well I can detect that, okay, will determine the sensitivity. If I have a peak which is indistinguishable from the noise in the signal, okay, then you will have low sensitivity. So I want as high peak value as possible compared with the noise. So the peak height over the typical noise, you can call it as signal to noise ratio. Okay, that is called sensitivity. But I should also not have a case where you have two peaks which are overlapping. Okay, if the two peaks are overlapping, then there is no point. I mean, the separation is not successful. So we also have to see how well separated two peaks are. The more this separation between the peaks, the better it is. So we call that as the peak resolution. So our goal is to have a certain amount of sensitivity while maximizing our resolution so that we can clearly identify this peak belongs to a particular different species and this particular peak corresponds to different species. So the resolution is the distance between two peaks divided by, you can think of this as the sigma is the standard deviation of the peak width, okay, half of the peak. So we want to maximize the resolution for a particular, and of course we also want better and better signal to noise ratio. So how we can achieve this, what we need to see. So now let's focus on the resolution. So there's little bit of formulas over here, but we can go over them. So think that your sample 1, the first peak has covered a distance L in time t. Okay. So what is the speed of this zone is the mobility of sample 1 mu1 times the electric field. In capillary electrophoresis, the electric field is uniform throughout the channel because the background electrolyte conductivity is much higher. Okay. So L over the velocity is the time that sample 1 has reached, sample 1 has taken to reach the detector. Okay. During this time, if you have some understanding of diffusion processes, okay, then we know that the peak variance, the standard deviation, the squared of the standard deviation of the peak, it actually grows linearly with time. Okay, it is characteristic of diffusion processes. Okay, molecular diffusion behaves in this fashion. So what we get is that the relative distance between two peaks will be, what will it be in time t? this is the relative velocity. The difference between the mobility is time electric field times t is the distance, the separation between the two peaks, and sigma is scales as under root 2 dt. D is the diffusivity of the ions, and let's say we are taking same diffusivity for both the ions. Okay, so my resolution, okay, scales as, so my resolution, it scales as this, okay, that is the difference in the mobility times electric field, and you have time and time cancels, and you have square root of time over square root of 2 times diffusivity. Okay, this is just a scale, this is not the exact value.
Can you explain sigma again?
This one?
Yeah.
Yeah, so the characteristics of a diffusion process. So see, you have diffusion in various systems. Okay, I'll give you a simple example. So let's say that I have a rod of metal, or let's say a spoon. Okay, and I have a flame. Okay, a burner in my kitchen. I put one end of the spoon on the flame. Okay, now the question is, after how much time will you feel at the other end that you'll start feeling a higher temperature? Okay, so what happens is conduction, heat conduction is also a diffusive process. So what you see is that if you look at, in that case, the length of your spoon, okay, the time, or you can, the time will depend upon the square of the length of the spoon. That means if you have 4 times longer spoon, or 2 times longer spoon, you will take 4 times more time. Okay. Similarly, in this case we have molecular diffusion. So if let's imagine the peak is initially very sharp. Okay, it's like a delta function, a very sharp peak. Okay, so sharp that we ignore the initial width. Over time, t, the peak standard deviation, will scale in this fashion. Okay, the peak width is going to scale as under root of t. Okay, that's the characteristic of a diffusion process. If you solve diffusion equation, okay, you can get this. Okay, but this is just a scaling. Okay. Okay, so because if you didn't have this square root behavior, then things will be very different. Okay, so what we see is that the peak, the resolution of the separation, okay, obviously depends upon how different the two mobilities are, mu1 minus mu2. If it is much higher, you will get better resolution. Obviously the peaks will be separated. Okay, if you apply higher electric field, you will get better resolution. If the diffusivity is low, for example, when you have you do electrophoresis of DNA strands on a gel, in that the diffusivity is very low, so the resolution is good. And if you do the separation for longer time, the distance is going to increase, okay, much faster than the peak width is going to diffuse. Okay. So this is about resolution, this is not about the sensitivity, because you can, what this says is that if you have separation for a longer time, okay, you can get better and better resolution, but your peak is also decreasing over time because the peak is diffusing, so the sensitivity is also going to go down. So there is a trade-off, okay, between resolution and sensitivity. And if you do further analysis, what you will see is that the the time is related to the length, okay, this peak takes to reach the detector, okay, or the length of the channel. So if you put this expression of time, what you see is that the peak resolution actually depends, okay, besides the mobility and diffusivity, depends only on the applied voltage, okay, because this electric field times length becomes voltage. So all that matters is you take as long, whatever length you want, okay, as if you apply a high voltage, you are going to get high resolution. So what happens is that glass uh, has some conductivity. It's not very high conductivity, but certainly higher conductivity plastics. And on a planar device, if you can apply very high voltage, the heat dissipation you can still control, and you can also put cooling blocks because of the planar geometry. So in microfluidic devices we can use very high voltages, okay, and it really doesn't matter you want a 1 meter length or a small length, the resolution will be similar, okay, if you apply similar magnitude of voltage, okay. So this is how we want to improve the resolution. We want to apply high voltages and resolution increases over time. But there are various mechanisms that occur, transport processes occur during the electrophoresis process, which can lead to reduction in the resolution. Okay, how we can have lower resolution? Okay, the main reason for reduced resolution is that there are some transport processes which are trying to increase the width of the zone. Okay, so if these peaks are dispersing, then you will have lower resolution, because resolution is defined as the relative distance divided by the peak width. Okay, another term is used in electrophoresis literature called plate height, but see, this is not a dimensionless quantity. So personally I prefer resolution because it's a dimensionless quantity, you have length over length. Okay, so now we have to see what are the various ways by which, in addition to diffusion, the peak can diffuse, okay, further. So if you have, in addition to electroosmotic flow, you have non-uniform flow in your capillary, okay, this could be due to imbalance of fluid on both sides of the capillary. Sometimes you also have Joule heating that can lead to some non-uniform flow. Then what you can have is, you can have additional dispersion of the analyte peaks, okay, and this mechanism that I am showing here is called Taylor-Harris dispersion, okay, and you can work out the effective diffusivity. The effective diffusivity is that if there was no flow, then what would be the diffusivity? Diffusivity is D, but if there is a flow, the effective diffusivity will be much higher, okay. We can work out this, but today I'm just going to explain the mechanism of Taylor-Harris dispersion. So let's see. So you start with a straight band, and let's say you apply a non-uniform flow. So what will happen? The solute in the middle is going to move ahead, whereas the solute at the channel walls is going to stay there, because my pressure driven flow has zero velocities at the end. It's not like electroosmotic flow velocity, plug shaped velocity. So you will have this distortion of a band. So essentially the molecules in the middle are going to get advected, the molecules at the end are not going to get advected. Now what happens is that you have very high vertical concentration gradients. So now you have very strong diffusion along the radial direction. So over time, okay, just because of the combination of advection in the axial direction and diffusion in the radial direction, this band is actually going to diffuse even further. In fact, if you have an analyte with lower diffusivity, it's going to have higher dispersion, okay, because first it's going to the band is going to distort much further, much more, and there are going to be very strong radial gradients. So the goal is that in microchip electrophoresis we want to avoid non-uniform flow, okay, we want to avoid concentration gradients, we want to avoid Joule heating. All of those can lead to non-uniform flow, which can lead to additional dispersion. That's one thing. Now we can look at the competition between signal to noise versus resolution. So what I told about resolution was I just gave you an insight, but in an actual process, okay, you can have the peak actually variance or the peak width depends on various factors. Okay, the peak width depends upon the amount of sample that you have injected. If the plug is initially wide, then the peak is also going to be wide. Okay, that's the first term over here. Okay, this is due to dispersion. Dispersion could be, it's again a diffusion phenomena, but now I'll replace diffusivity with effective diffusivity. The first one is the variance of a plug of half width h. Okay, and then you have some variance, some peak width due to the detector width also. So imagine like this. Okay, I have a detector of finite size, and there is a thin line, that thin band that is moving over the detector. Just because my detector is wide, okay, it's also, your thin band is not going to appear to be thin, it's going to be appear to be diffused. Okay, just like you have a frosted glass and you shine a laser pointer from the back, it's, the pointer is going to look a bit more diffuse. So this is this term. Okay. So if you incorporate all of these things in the model, okay, so what you can see is that, okay, this dotted line is, I'm plotting signal to noise ratio versus length, and I've non-dimensionalized the length with the detector width. Okay, this I've taken from this from a model, but qualitatively is what you can understand. So you all understand that signal to noise ratio is going to reduce over time. The noise remains the same in the detector, but the peak is going to diffuse over time. Okay, peak cannot increase, otherwise it will violate the second law. Okay, of thermodynamics. So you can only have, entropy is only going to increase. You can you will have more diffusion over time. Okay, whereas the resolution keeps on increasing over time. So what we have to do is that we want good resolution and good signal to noise. So if you plot the signal to noise and resolution on an axis where you have on the vertical axis the initial plug width versus the length to the detector, you will get a diagram like this. Okay? And there's only a particular zone where you can get good signal to noise ratio and good resolution. Okay, to understand this, first we know that if you are over here, okay, and you keep on increasing for a given plug width of the initial sample, okay, if you increase the length, the resolution is going to improve, but the signal to noise ratio is going to decrease. Okay, if you have a fixed length of the capillary till the detector and you increase the plug width, imagine that the initial plug width is so high that, okay, so let's say the initial plug width is so high despite the electrical conductivity of the solution. Okay, electric field is actually the current density over divided by the conductivity. Okay, so in high conductivity solution the electric field is less, in low conductivity solution the electric field is high. So what these ions, while they move towards the left, they feel that the ions in front of them, once they reach the high conductivity zone, have low velocity, while they are coming at very high velocity from behind. It's just like you have a traffic jam. In what will happen, these ions are going at that place, concentration will increase over time. So here I'm showing this experiment. So what you see is, look at this. Okay, here ions are moving towards the left, but electroosmotic flow is moving, taking everything towards the right. Okay, so you see that the initial concentration was low, but the concentration of the fluorescent species has increased over time, and what you see, the motion towards the right, is due to flow, not due to motion of ions. The ions are moving towards the left, electroosmotic flow is carrying towards the right. So what we have done is, the initial concentration we have increased. Okay, we have pre-concentrated the sample. Okay, now what we can do is we can combine this field amplified sample stacking with capillary electrophoresis. So what we are going to do is that we are going to have a low conductivity sample and a high conductivity background. Okay, so now this initial sample over here was of lower conductivity, so initially the concentration increases, but then you will have separation. Okay, in a later lecture I will show a detailed simulation of how we can design this process, but we can increase the sensitivity, because first we are trying to stack the samples and then we are going to do separation of these species. So with this we come to the end of this lecture. So I hope by through this lecture you have use a cross-shaped microchannel to perform capillary zone electrophoresis. I have tried to show that there is a trade-off between resolution. You want to have separation as you want, but if you increase the resolution, the peaks are going to diffuse further. So the sensitivity will increase over time. So we need to do an optimization to find we can get good resolution and good peak sensitivity. We have seen that there are various ways by which you can have decrease in the separation resolution because of dispersion of sample zones. And you can have non-uniform pressure driven flow, which can lead to Taylor dispersion. Okay. Then we have the initial plug width is also going to affect the resolution, so we can control the initial plug width. Any geometric defects or turns in the geometries or the channel going to lead to dispersion. And finally, we've touched upon a phenomena called electromigration dispersion, which is a nonlinear electrophoresis phenomena, which we'll discuss in far more detail in the forthcoming lectures. What I have not discussed in the initial lectures are what are the ways we can detect the samples. So in the next lecture on ITP, we'll look at some detection methods. So the same detection methods apply to any electrophoresis technique. Move that part to the next lecture. So with this, we'll come to end of this lecture. If you have any questions, I'll be happy to take any questions.
The last aspect is not very clear.
That I will, I just touched upon that. I'll explain it in more detail later on. So the idea is that the initial sample, let me go back and so the way to implement that is that this sample, okay, the conductivity, you can take low conductivity than the background conductivity. So what will happen is that in this initial step, you have high electric field here and low electric field over here. So these ions are first going to stack together and the concentration is momentarily going to increase. So you start, even though initial concentration of the ions is low, you increase the concentration before separation. So that we will discuss in later lectures. Okay, if any other question? So if no more questions, then we can stop here. Right?
These kind of principles are working into that sugar testing and
no. So sugar, that glucose testing.
Testing strips and
No. So glucose testing is based on electrochemical detection. Okay. Yeah. So there you have, if I'm correct, there's an enzyme called glucose oxidase. Okay, and there is an electrode. So when the oxidation process takes place, so you have oxidation is what? Loss of electrons. So electrons flow through the circuit and you count what is the charge that is transferred. So that's a completely different process. Here that's an electrochemical process on the electrode. We are talking about the motion of ions within the bulk solution. The only electrochemical reactions that are taking place are at the electrode, which will lead to electrolysis. Okay. Yeah. Okay, so we can stop here. Yeah. So we are behind schedule.
Yeah.
Significantly. Yeah.
None of the other days have run on schedule.
Is it?
So I thought it was my European background that was looking at the clock all
Yeah.
the time. So.
Yeah, I was here by 9 and then there was I thought that I'll set up my system, but I couldn't find him. ठीक.
We can start.
Can we get started?
Start and see if there's a natural cutoff point somewhere around 1, so we will go for lunch. Then we see what the afternoon break is.
Maybe 1:15.
Oh, most days we've stopped around 1:15 and then get back.
Okay.
I think the rest will be showing up. Will be showing up around 1, 1:15 to get us to lunch.
Yeah, but we have to cover 5 lectures, right?
Yeah, as per the schedule.
Yeah. So let's see how it goes.
See how far you come, and otherwise cut something out of this.
Yeah. Okay. Start. Okay. So yeah. So now in this lecture, I'll talk about another electrophoresis technique called isotachophoresis. I'll abbreviate it as ITP, and we are going to discuss theory and some applications. So the previous lecture we discussed microchip electrophoresis. So understanding microchip electrophoresis is rather easy because the motion of the ions and or you can say the motion of the analyte zones while separation, it's decoupled from the electric field. Okay, only towards the end we saw that if there is a coupling, you can have peak broadening, sharpening, those kind of things. Okay, but ITP is very different. Okay, ITP, the motion of the analyte zones and the local electric field is strongly coupled. Okay, only because of this coupling we get this technique. So it's a bit challenging to understand, but if you are able to get something out of this lecture, I will be happy. The math is a bit challenging. I have something on slides, but I'll try to avoid as much as possible so that I can give you some intuitive understanding of how this process works. Otherwise, you need some background in mathematics to understand why you have this kind of nonlinear behavior. So again, just to recap, we are looking at electrokinetic transport. Okay, that is transport of ions and fluid by applying electric fields. So again, in this kind of systems, we have a capillary of dimensions, typical width of 10 micrometers, even 100 micrometers. Most of the time we use glass, but we can also use polymers like PMMA or PDMS. And in these experiments, we have electroosmotic flow, but primarily for ITP, we just need to focus on electromigration, because flow is just going to translate everything in the direction of the flow, but electromigration is the main phenomena responsible for the process I am going to discuss in this lecture. Okay, and this slide is crucial. Let's not worry about math and all. I think most of you are from chemistry, analytical chemistry background. I have these on slides, but we can skip it. Okay, so let's recap. Okay, what we have is that if you apply electric field, okay, then the velocity of ions is proportional to electric field. Okay, there are some species which have nonlinear behavior, but let's just use the simplest behavior. The velocity is proportional to electric field, and the proportionality constant is called the electrophoretic mobility. Okay, typical value of electric field that we'll apply, the magnitude of electric field will be about 10 kilovolts per meter. That means for 1 centimeter long channel, you apply a voltage of 100 volts, okay, DC voltage. And typical value of mobility is about, in SI units, is about 3 into 10 to power minus 9, okay. Uh, and that means if you uh, multiply this mobility with the 10 kilovolts per meter electric field, you will get a velocity of about 300 micrometers per second, okay. That is the typical velocity that you will see. Now, what we are going to discuss is how we can generate self-sharpening concentration gradients in electrophoresis. If you recall, in capillary zone electrophoresis, we had analyte zones which were moving, but they were also diffusing, okay. And because of diffusion, the sensitivity was reducing over time. So, can we find a way where we can counter diffusion? Okay, we can stop diffusion, or we can work against the diffusion so that the zones do not diffuse over time. Okay, the way to do it is using nonlinear effects in electrophoresis, but I'll just try to show you a representative simulation, which a visual description of what happens. But let's see how we get sharp gradients in a capillary, okay, in capillary electrophoresis. So what we do is this, okay. Let's say that you have a channel, okay, a capillary. You fill it with an electrolyte, okay. Electrolyte will have negative ions and positive ions. So let's say that we fill it with sodium chloride, okay, although I would not use sodium chloride otherwise, but because it's not buffered, but let's say it is salt mixed in water, okay. So you have counter ion is sodium, so we C denotes counter ion. So you have sodium is the positive ion, the cation, and the chloride ion is denoted by L over here, okay. So you fill it in the channel, but on the left hand side you clean up the inlet and you fill, let's say, sodium acetate, okay. So sodium is present, the cation is the same in both the solutions, but here you have chloride ion in the channel and you have, let's say, acetate ion in the reservoir, okay. Why I have chosen chloride and acetate? Because the chloride ion in absolute terms, it has higher mobility than the acetate ion, okay. So let's say L ion is the leading ion, okay, which has higher mobility. T ion is the trailing ion, which has lower mobility, okay. So now what we do, this is the initial condition. Now we apply electric field. We apply electric field towards the left hand side because we want negative ions to move towards the right, okay. So what's going to happen, okay, if you think, okay, in a layman terms, okay, negative ions, chloride ions are going to move towards the right, right, of course, and acetate ions are also going towards the right. If the electric field were the same in both the zones, then which ion will move faster? Chloride ion. So chloride ion will move faster and the acetate ions will not be able to catch up, okay, if we think that the electric field is constant, okay, or uniform. But that doesn't happen, okay. You can't have a separation of ions in that sense. So what happens is that the conductivity of the solution behind the chloride ions is going to change in a way that the electric field will increase, okay, behind the chloride ions, so that electric field times mobility of the trailing ions is going to be same as that of the speed of the trailing ions is going to be same as that of the leading ions. I'll show you a video and then that will give a clear picture, okay. So imagine that blue ions are the chloride ions, red ions are acetate ions, okay, and I apply electric field. This is just a approximate simulation I have done using imagining them as particles, okay. So what do you see? This is the initial concentration of the trailing ions, the red ions, the blue ions are moving towards the right, but this interface has sharpened. Okay, this interface remains sharp. Okay, let's go back. Okay, now let's see. So I have chloride ions over here, the leading ions, and I have significantly higher concentration of leading ions over here, shown in blue color. I have low concentration of the trailing ions. One example is acetate ions. Now I apply electric field. Okay, it's not that blue ions are going to move ahead and red ions are not going to catch up and there is some white space in between. That doesn't happen. Okay, instead what happens is that the electric field behind the zone, okay, it changes, the concentration changes, the concentration of the red ions changes, which changes the conductivity of the solution, which changes the electric field, because electric field times conductivity is a constant which is called the current density, okay, the total current divided by the cross section area. So the concentration adapts behind the chloride ions so that the speed of the chloride ions and the acetate ions remains the same, and this initially diffusive interface between two zones sharpens over time, okay, and remains sharp and just propagates towards the right. So now let's see how it works. Okay, so you see that this sharp interface is forming and it's moving towards the right, okay, and if you just look at this interface, the ions, the blue ions moving towards the right and the red ions moving towards the right, they have the same velocity, because if they don't have the same velocity, then the red ions are going to overtake the interface and the blue ions are going to stay back, okay, or go behind this interface, but that doesn't happen. So what actually happens is that, okay, the physics governs that you have a sharp interface that forms, the initial concentration of the ions, it changes, okay, and it attains a constant value which depends upon the ion concentrations in the channel, okay, and there is a sharp interface that propagates, okay. This interface will remain sharp as long as you apply electric field. As soon as you stop electric field, you will have see diffusion of this interface. So how can you generate this sharp interface? The way to generate sharp interface is to have a high mobility ion filled in the channel ahead of low mobility ion, okay. Only then you will get this sharp interface. If you have if let's say this T ion has, or the trailing ion has higher mobility than leading ion, it's going to overtake, okay, the blue ion. So you will not get a sharp interface. Okay. So this forms the basis of the separation technique called isotachophoresis, which we call as ITP. Okay. So the difference between ITP and zone electrophoresis is that in electrophoresis we have a uniform background electrolyte. Here we have a discontinuous electrolyte system. You have a leading electrolyte consisting of high mobility ions initially filled in this channel, and you have low mobility in the trailing electrolyte, and you can have a common counter ion, just like in the example I have given, okay. So that is what we have to see, that how we can use this kind of sharp self-sharpening gradients or interfaces for our advantage for separation and reconcentration. So those who are slightly more mathematically inclined, okay, will appreciate that this interface, any interface or any front that sharpens over time, okay, you can think of it as a shock wave, okay. We know you have some shock waves in aerodynamics, okay. Similarly, we have shock waves in ions, okay. These are just interfaces which sharpen over time, they have a self-sharpening property, okay. And why is this self-sharpening? Because let's say that the blue ion somehow is kicked to the red zone, okay. Now the blue ion is going to see itself in a zone where other ions are moving slower, so it's going to move ahead. If the red ion gets to the blue zone, it's going to find itself in a zone where all other ions are moving faster. Okay, so they move at the same speed in their respective zones, not in each other's zones, because the electric field in the red zone is higher than the electric field in the blue zone. Okay, so this is one interface. This technique or this kind of interfaces we see in a technique called isotachophoresis or ITP. So the main difference between ITP and electrophoresis is that we use discontinuous electrolyte. So we have a leading electrolyte which has a high mobility co-ion, okay, and a trailing electrolyte which has low mobility ions, and the counter ion is the same. Okay, for simplicity we can have the same counter ion. Okay, now how we can use this kind of self sharpening gradients for separation and pre-concentration. So recall, what did you see in the previous simulation? Okay, there were two effects. There were two effects. One is this interface is very sharp, it's not diffusing over time. Okay, other is that this low concentration of the trailing electrolyte is adapting and the concentration is increasing. Okay, okay, it's, you can think of it as that some system has some memory of what was initially filled in the channel. Okay, so if you had high initial concentration, whatever ions are displacing the high mobility ions, their concentration is also going to increase or adapt to a higher concentration. This is characteristic of ITP. So adapting new concentration is proportional to the leading ion concentration and sharp interfaces. These are two characteristics of ITP. So now let's see how we can do a typical ITP experiment. So now what we do is that, okay, we have a leading electrolyte, okay, with high mobility ion, a trailing electrolyte with low mobility ions, and then for electroneutrality we have a counter ion. Okay. Now what we do is, in the previous example we just had this Le and Te, leading electrolyte and trailing electrolyte. Now we initially we dispense some analyte mixture, some sample between the leading and the trailing electrolyte. So my concentration versus X looks something like this, Le, Te, and initially you have a diffused zone where you have two types of ions. Okay, and now at this point the voltage is not applied. Okay, the circuit is open. Okay, so now what we do is we apply electric field. Okay, we apply voltage. So what's going to happen? Okay, so we see that you can get sharp interfaces, but what I have done over here is that I have chosen Le and Te, okay, in a way that the Le ion mobility, the co-ion mobility, is the highest among all the ions over here. The Te ion has lowest among all the ions. S1 sample has higher mobility than S2. Okay, so what happens is when you apply electric field, okay, you will get a picture like this where you have, see there are two effects going on. Okay, so S1 concentration is relatively low over here. Okay, it's when S1 displaces the leading ion, its concentration is going to adapt, it's going to increase and becomes proportional to the Le concentration, and these diffusive interfaces are going to become sharp. So what you get is, if you just ignore this left part, just look at this. Okay, so you have Le and sample. Okay, this you have attained a plateau of the sample concentration attains a constant value like we saw in the previous simulation. This interface is very sharp. Okay, it's not diffusing over time, it's sharp, it's propagating, it remains sharp as long as we apply electric field. Okay, okay, now what we have is S2 was in had the sample S2 initially had a relatively low concentration, so it could not adapt to the maximum concentration. If you have more amount of sample, it would have adapted and attained the maximum concentration that is allowable. Okay, and then its zone will start expanding. So we have two types of zones over here. We have one zone which is of plateau shape,
okay, other is of peak shaped. It depends upon the initial amount of sample that we have, and there is a sharp interface of TE, the trailing electrolyte, with the sample zone. Okay, so as I said, all these boundaries, this boundary, all the boundaries, okay, are the boundaries between the adjacent zones are self-sharpening in the nature. Self-sharpening in nature. That means you stop the experiment, you stop the voltage, remove the voltage, it's going to diffuse. You apply again, they are going to become sharper again. Okay. The reason is that as long as you are applying electric field, okay, the high mobility Le ions are always going to lead the trailing ions, and low mobility ions, in this case, okay, for this interface you have a leading ion and sample ion. The slower ions are always going to lag behind. But despite having different mobility, the speed is the same, because local electric field in the leading zone is lower than the local electric field in the sample zone, and the local electric field in the TE zone is even higher. Okay, so that the velocity is the same, okay, just because the electric fields are different. Okay, so the net effect is that you can get purified zones. Okay, you get zones where you just have S1, you just have S2, okay, and these interfaces are sharp. So as long as you do experiment, you will not have dispersion of these zones. Okay, so we can just classify, because in certain literature they'll just classify in two types. Okay, so if the initial concentration is high enough, then you will attain the maximum concentration that is allowed. We can call it as a plateau mode, because it looks like a plateau. If the concentration is initial amount of sample is not high, okay, you will just see a peak rather than a plateau, rather than a broad plateau. Okay, and this distinction just helps when we discuss the way we are going to detect these zones. Okay, so what do you see in a typical experiment? So we have, imagine that you don't have 2 samples now, let's say you have 10 or 12 samples, okay, 10 and different species in the initial mixture. So you will have various plateaus, okay, you will have various plateaus, okay, and these zones are migrating. Okay, so what you can do is, the easiest way is that you put a conductivity sensor at the end. Okay, you can measure the resistivity of the local resistivity of the channel and measure the conductivity as these zones move over that detector. So you may record a signal something like this. This is resistance versus time. Okay, so in this particular case, what you are seeing is, you are not seeing peaks. Okay, in electrophoresis, in microchip electrophoresis, in zone electrophoresis, what you detected was peaks. Okay, peaks that are separating over time, whose resolution is increasing over time. The distance between the relative separation between the peaks is increasing over time. Here the relative separation will not increase over time. Once the samples have purified, okay, you will see plateaus. Okay, because the leading electrolyte has highest conductivity, so it has lowest resistivity, local resistivity. The next zone has slightly higher conductivity, slightly lower conductivity, I'm sorry, and the resistance is higher. So you will see a signal like this. Okay, so like electrophoreogram, you will have an ITP signal, isotachophoreogram. So based on the plateau heights, okay, you can, in the signal, you can identify which sample do you have. Okay, so in this particular case, okay, if whether you can distinguish one plateau from the other defines the resolution. Okay, in ITP, okay, the zone width corresponds to sensitivity. Longer the zone width, that means you have more amount of initial sample. Okay, and if you are able to detect a longer zone, okay, that you can correlate it with the initial amount of sample that you have. Okay, and resolution is depends upon how well you can distinguish one plateau zone from the other zone based on the local properties, in this case that is resistivity. Okay. So, the benefit of this process is that you do not have decrease in signal to noise ratio over time. The sensitivity does not decrease, okay, but the resolution is limited. The resolution cannot increase over time. In zone electrophoresis, the peak separation would increase over time as long as you do the experiment, but the sensitivity would go down. Okay. In ITP, the sensitivity will not go down, sensitivity will remain the same over time, but the resolution remains fixed. Once you attain steady separation, you will not see increase in the resolution over time. Okay. So some distortion over here, but we can ignore this. So why do we want ITP? Okay. So with ITP, what you can do is, there are two things for ITP you can use for. Okay. One is as a pre-concentration method. Okay. Let's say you want to do capillary electrophoresis and you have a trace amount of sample in your original mixture. Then what you can do is that you can use ITP to focus the sample in a zone, because the concentration increases over time. Okay. Concentration can concentration is some proportionality constant times the Le concentration. So the idea is that if you have some charge in the capillary, you are displacing that charge, okay, those ions with other set of ions, those ion concentrations will be proportional to the concentration of ions that you are displacing. So what happens is that the initial concentration becomes high, okay, and you can use cheap detectors for detection. Okay. And unlike capillary zone electrophoresis, okay, where in the previous lecture I said that the zones will distort over time. Okay, in this case the zones are not going to distort, they are going to locally distort, but again because they are self-sharpening in nature, as soon as the electric field becomes uniform, the zones will regain their shape and you will get a steady state. Okay. Another point I'll come to it later on is you can devise new ways of detecting these zones using the displacement physics, how these ions behave when you put them in an ITP experiment. I'll come to this soon. Okay. So the key difference is that, okay, from microchip electrophoresis or zone electrophoresis is that the resolution is not going to change over time, okay, but the sensitivity does not decrease over time. So you can get high sensitivity because the signal will be very high, okay, but the ability to distinguish one zone from the other is not going to increase over time in capillary zone electrophoresis. So ITP is, I just put a brief background of ITP. So ITP has been known for quite some time, okay, from 19th century, and it was widely used, okay, for various analytical chemistry applications, but in 2000s with the advent of microfabrication, it has seen renewed interest for various microchip electrophoresis techniques, and particularly for pre-concentration of samples prior to capillary zone electrophoresis. Okay, so it's not something very new, it's pretty old, the physics is well understood. So let me try to explain the physics. Okay, there's some math, but we can ignore if you are not familiar with. So most of you have chemistry background, isn't it? Yes. Yeah. So let's not go into detail, but some physical understanding, at least the names of the laws that go into describing the physics is essential. Okay. So because I want to introduce you to this, because we also have to look at my next two lectures are on modeling and simulation. So we can't do simulations without understanding the equations, right? So we have to understand a little bit. So we need to model this phenomena and understand why you get sharp interfaces, okay? Because they defy otherwise, our usual observation that you have an interface between two liquids and it will diffuse. So why is it self-sharpening in nature? So what we do is that let's look at a very simple model of ITP. So what we say is that we take a small region over here and see how the ion concentrations are changing. So this is a control volume, a small element over here. The concentration, the rate of change of the amount of ion I, okay, species I, is given by this, okay, and you have some mass flux of ions from the left hand side, some mass flux on the right hand side, okay. So if you ignore diffusion, okay, the flux is due to the ion velocity times the concentration, that's the mass flux, okay. So if you put all of this together, you get an equation, a partial differential equation, which says that the rate of change of concentration is equal to the gradient in the mass flux, okay. If more amount leaves than what is coming in, then the concentration has to drop, okay. Or if more amount enters a small region, okay, than what is leaving, then the concentration is going to increase. So what you have is, okay, you have equations for the ion concentrations. We have three types of ions for the system shown over there. We have the leading ion, we have the trailing ion, and the counter ion, okay. So there are three equations. Another constraint is that electroneutrality. You can't have unbalanced charges anywhere, okay. If you have you can say the valences times the concentration of ions, okay, and sum over that has to be 0, okay. You have to have same number of negative ions as same number of positive ions in a particular region everywhere, okay. So another thing is that you put all this together, what you will get is Ohm's law, okay. Ohm's law just says that if you have high conductivity, then the electric field is going to be low. If you have low local conductivity, electric field is going to be high. And what is conductivity? Conductivity is dependent upon the concentration of ions. If you have more ions, the conductivity is higher. If you have less ions, conductivity is lower. You make more concentrated solution, it has higher conductivity, okay. You put all together, you get some equations like this, okay. We will not spend much time, okay, but the main thing is this function, okay, which in analytical chemistry is well known. It's called Colorosh regulating function. So let me see how to explain if you don't have significant background in mathematics, but essentially you have three governing equations for three types of ions, three species of ions, and you have two algebraic relations. One is the electron neutrality and one is Ohm's law. So what you can do is that you can work with one equation only, one differential equation, and then you can use Ohm's law and you can use the electron neutrality condition. But what you get is, if you rearrange these equations, just focus at this equation, okay. It says that this function within the bracket, within the parenthesis, never changes over time, okay. This is called Colorosh regulating function. It is a function of the valences. So if you have sodium ion, this Z is +1. If you have chloride ion, this is -1 times the concentration divided by the mobility. If you sum all of them, okay, then this function, okay, value does not change over time, That is what Colerash regulating function is. Okay, so the point is this. Okay, so you fill your capillary or the microchannel with your leading electrolyte, okay, and you will get some value of this function, the Colerash regulating function KRL, okay. But when the leading ions are displaced by the trailing ions, okay, this function value remains the same. So let's see. Okay, so initially you have the trailing ions over here, okay. So the value of this function k in the brackets is this, okay. You don't have any trailing ions, you have only leading ions. So valence of the leading ion times the initial concentration of the leading ion divided by mobility plus the valence of the counter ion times concentration of the counter ion divided by its mobility. This is the value of the Colerash function KRF, okay. But when the sorry, this is when the let's see, when the trailing ions displace the leading ions, okay, the value should not change, okay. So the left hand side of the equation gives the Colerash regulating function value, okay, when you have trailing ions instead of leading ions, okay, and then you have electroneutrality condition also. So if you work out, what you get is, you work out the concentration, you see that the trailing ion concentration is proportional to the leading ion concentration. So practically what it means? Practically it means is that, let's say that I have, let's say 100 mic acids, okay, and then I apply electric field. In which direction should I apply electric field? These are acids, okay. Acid means there, once they dissociate you will get anions, okay. So anions are going to move towards the positive electrode. So I have to apply, take positive electrode on the right hand side, apply electric field in this direction, and negative ions are going to move towards the right hand side, okay. And for this simulation I have chosen some current density. So let's see if I am able to show the simulation. Okay, so once you apply electric field, you see that, okay, the faster ions, okay, the faster of these ion is going to move in front, okay. The ion with lower mobility is going to lag behind, okay, and then they will get ordered into zones of different zones ordered by their mobility. So you have high mobility ions on the right hand side, low mobility ions on the left hand side, and different have only one so they this zone does not have other species, okay. So you can purify them and this interface remains sharp as long as you apply electric field, okay. So if you have a complicated geometry, you want to take sample from one side to the other side, you can use ITP for that also. Okay, so that is how ITP works. Okay, when we look at this picture you will get, you know, complete separation only after a particular distance. But once you get complete separation, this whole pattern is just going to migrate. It's not, the zones are not going to diffuse over time, okay. As long as you apply electric field, they are just going to migrate. So that is that is an ITP. Okay, you can use it for analysis of small ions in some samples. I'll give like some examples today, but in my work we use extensively this for DNA analysis. Okay, how we have done it, I'll try to show. But the question is that doing ITP experiment is not easy. Okay, capillary zone experiment is relatively easy in that sense that you can choose, and all you have to do is you have to choose a background electrolyte. You don't have discontinuous electrolyte, you don't have two electrolytes, you just have one electrolyte. All you have to ensure is that you have the required pH that you need for your samples and the concentration is high enough that its concentration is greater than the sample concentration. But ITP is all the the zones are very robust, they are not diffusing over time, but getting the electrolytes in the first place is the main step, okay? Because all what you have to ensure is that the leading ion has highest mobility, trailing ion has lowest mobility, because if they don't have high and low mobility than the sample ions, then the sample ions are going to either overtake or trail behind. You will not get this focusing behavior. So typically this is how, this is an easy way to uh, choose electrolytes for ITP. Okay, so what we do is that, okay, there are various types of electrolyte systems. The easiest one is this. Okay, so what we do is that, let's say for anionic ITP, if we want to separate and pre-concentrate negatively charged species, we take an Le ion, which is an ion of a strong acid. So what we'll do is we'll use chloride ion. Chloride ion has very high mobility, okay, among highest mobilities of among small ions, okay. And we use a counter ion which is a weak base, okay. So we have a strong acid, okay, and we have a weak base. So we'll have maximum buffering at what concentration ratio? So if I want to have a buffer, I want to make a buffer, and let's say I put 2 times of 2x concentration of the weak base, let's say 20 millimolars of the weak base and 10 millimolars of the strong acid, what will be the pH? pH will be equal to pKa of the weak base. Okay, if you can work out, okay, that's just a thumb rule. So you want to make pH 8.1, okay, approximately, which is pKa of trace. You let's say 10 millimolar of HCl and add to it 20 millimolar of trace, and you get pH of 8.1. Okay. Now what you do is, I want a Te ion, a trailing ion with very low mobility, but it's very difficult to get ions with very low mobility. All small ions have similar order of magnitude of mobilities. Okay, so what we do is that we choose a Te ion, okay, which is a weak acid, okay, which has pKa which is greater than this value, in this particular case, greater than the pKa of trace, the counter ion. So what we have is, if I have a weak acid and the pH is not very high, then what I'll get is, we'll get very low ionization of that acid. So because you have very small amount of acid in ionized state, the mobility is going to be very, very low. So you can use that as Te ion. So let me give an example. Okay, so what you can do is, when I try to do experiments, I'll by default, easiest choices for me is to use chloride ion as the leading ion, because it's fully ionized, it has high mobility. Okay, I'll try to see the samples, what kind of pH my samples need. So let's say you want pH around 7 or 8, you choose the counter ion accordingly. If I need pH about 8, I use trace, and I have 1:2 ratio, so pH is equal to pK, so 8. Okay, so Le is all sorted out. Te ion is what I have to figure out. Okay, so now what I do is, you see, I have various options of Te ions. Okay, so this is mess, mops, heaps, tricene, and in the brackets I am giving the pKa values of those. Okay, in the rows I am giving the counter ion. So trace will give you a pH about 8.1. Okay, is that fine? 8.1. So what happens is that, let's look at this. Okay, so if you use trace, pH of 8.1 with a weak acid having pK of 6, it will be more or less fully ionized, so mobility will be high. Okay, but as the acid dissociation constant or the pKa value increases, that means you have weaker and weaker acid, the mobility is going to decrease significantly. Okay. So what we do is we fix the pH first, and then you choose a weak acid as the Te ion, and then you can tune the mobility. So that's how we decide the buffers. Okay. And then we can detect the we can do it, and now we have to do the detection. So let me show you this experiment. Okay. So one way is that the ions itself are fluorescent, then we can directly detect them. So what I'm showing you over here is an experiment, okay, where the Le ions are not fluorescent, trailing Te ions are not fluorescent, but I have focused a fluorescent species over here, and you see that the concentration is pretty high. Okay, the signal is good and it's focused in a very narrow band. Okay. Similarly, in the experiment below, okay, what I have focused is double stranded DNA, okay, which we are visualizing using cyber green. It's an intercalating. So you start with a low concentration of DNA, you can concentrate them in a very narrow zone, but the concentration will increase. Okay, the DNA fragments are not going to get replicated like in PCR, but only thing is we are just focusing them in a narrow zone. So we can, if the analytes are fluorescent, we can always detect them using fluorescence detection. Okay, what if the analytes are not fluorescent? Okay, then what can we do? So there are various ways. One of the methods is that there's an indirect way of fluorescence detection in ITP, because ITP allows you to do this. So what we do in our experiments is that we put a fluorescent species which does not focus in ITP. Okay, so let's say that I put a fluorescent species which is even faster than the leading ion. So what will happen? It's going to overtake all the zones. Okay, but its concentration is going to adapt to the local electric field. Okay, because different zones have different electric fields, so the concentration is going to adapt, and that concentration will give you different zones, a different signal in different fluorescent intensity in different zones. So you can see these plateaus. Okay, even though your focused analytes are not fluorescent. Okay, it's an indirect tracer that we have put, which gives us indirect detection. So let me just put everything together and show you how to do an experiment. Okay, we take a microfluidic device. In this case, you don't need cross chip or anything. You just need a single capillary. Okay, you put your leading electrolyte and the non-focusing tracer. Fill the channel. Okay, from this side you fill your TE, and you can also add the sample in the TE itself. Okay, then what you do is you apply electric field, fluorescent intensity at a particular location over time. Okay, so just for general audience, in this case what I did was I just put lemonade in as my sample. Okay, very small amount of lemonade. So what I got is, if I didn't have this lemonade, I got some signal. Okay, like this between Le and Te. Okay, then this is one, Le and Te. Then with lemonade, okay, I got this large plateau. Okay, very large plateau. We repeated the experiment 3 times. You see that there is some additional zone that is showing up. Okay, and then I spiked the sample with citric acid, so this zone increases. Okay, so maybe that is because this zone is of the citrate ion. In this particular experiment, I have chosen Le and Te in a way that only citrate ion focuses. Okay. Okay. But what we did was that we, when I was at Stanford University, we worked on a system which was a handheld portable device where a small microfluidic device would go, and we would use ITP for detection of various toxins and pollutants, environmental pollutants. So what we would do is that we would use these fluorescence techniques, and the benefit of this ITP compared with electrophoresis is that the device is very simple. All you need is a single channel, okay. And another thing is that the sensitivity is always high, okay. Your sensitivity does not decrease over time. So it has various applications, okay. We worked for some detection of explosives, okay, and then we looked at some environmental pollutants in river water, and we also just to show that what are the concentration, what are the pre-concentration capabilities of ITP, we can also actually detect picomolar amount of sample, okay. That's very small amount, low concentration of analytes that can be detected in ITP, okay. So let me tell you how much is 1 picomolar. Okay, 1 picomolar is that if you take a grain of salt and you dissolve it in an Olympic size swimming pool, that is the concentration that you get, okay. And if it is fluorescent species in ITP, people have shown that you can focus it and detect it, because you can keep on increasing the concentration, focus for as long as you want, so that the concentration adapts to the concentration of the leading eye, okay. So that's with fluorescence detection, but you can use other methods of detection also. One is conductivity detection. What is conductivity detection? As I said, as the zones move past the detector, if you are measuring the local resistivity, every zone has a different electrical conductivity. So if you can measure the resistance, then you can measure what is measure the changes in conductivity of the solution as the zones pass by. So you can measure the signal or resistance versus time like this, okay. So one easiest way is that you just poke the electrodes within the solution and measure the conductivity. That's called direct conductivity measurement, okay. But it has its drawbacks. You are actually your electrodes are touching the solution, and you'll also have some electrolysis. So an alternate way is called capacitively coupled contactless conductivity detection. In this, you detect the change in capacitance. So what you do is that, which is related to the conductivity of the solution. So in this case, the electrodes are patterned outside the channel. They are not in contact with the solution, and by applying AC frequency, you can actually measure the change in the signal and estimate what is the conductivity of the solution within the channel. That's contactless conductivity detection method. But among all these detection methods, fluorescence has the highest sensitivity. Okay. So let's see how much time we have. Okay, so how much time do we have? We can.
I suspect this one will be between 1 and 40 plus 1, so.
Okay, so we can. Yeah, 15. Okay, so now let's look at ways by which we can improve the sensitivity of ITP. Okay, if you recall, okay, how good or how sensitive my detection is depends upon the width of the zones. Okay, because let's say that the width of this plateau zone is very small, okay, then it is going to be difficult to detect. Okay, so the longer the zones are, the better it is. Okay, so that will determine the sensitivity. In this case, the resolution is how well we can distinguish one plateau concentration from the others. Okay, so we want longer and longer zones, okay, wider and wider zones, if we want to improve the sensitivity of detection. What we do is that, okay, the easy way to do it is that we use channels which are not straight but have converging and diverging cross sections. You have a thick channel, okay, merging into a very narrow channel. So what you do is that if you try to simulate this, this is just for illustration. So initially you have very narrow zones in the thick channel. The larger cross section channel allows you to load more amount of sample. Okay, and when they enter the narrow cross section region, that large amount of sample, the peak concentration does not, the zone concentration cannot increase, right? It's limited by the LE concentration, so the width of the zone will increase. So the point is that in the same amount of length, having a large cross section channel in the beginning allows me to load more amount of sample, okay, but I'm going to see much wider, okay, because okay, for mass conservation, okay, if the cross section is smaller over here, the zones have to broaden. Okay, so we can do these experiments with this. Okay, another way to do it is called another way to increase sensitivity is called cascade ITP. Okay, so cascade ITP is essentially you create a concentration gradient between the leading electrolyte. So what you do is this. Okay, you have initially you have high concentration Le, and then you do ITP, but later on you move it to a channel where the concentration is low. So what happens is high concentration of leading electrolyte allows you to pre-concentrate more amount of sample, but once it goes to the low concentration Le concentration, so this, see, initially you get very high concentration plateaus, okay, but the width is smaller, but when it goes to low concentration Le zone, the plateau concentration decreases but the width increases. So there is a trade-off between the width and the height of these plateau zones. So the point is that with high concentration leading electrolyte, you can load, you can pre-concentrate more amount of sample, okay, and for with low concentration leading electrolyte, you can get wider and wider zones. So people have tried to do this also. Now what I want to show is that we can now combine what we have studied in both the lectures to our advantage. So if you recall, what is the benefit of capillary zone electrophoresis? The benefit is that you can improve the resolution as much as you want. Okay, you have longer separation time, higher voltages, and you will have larger and larger distance between the relative separation between the peaks, right? But the drawback over there was that the peak height would decrease over time. Okay, ITP on other hand has very high sensitivity. You can increase the concentration by a millionfold, but the drawback is its resolution is very low. It's very difficult to detect one zone from the other because the resolution, unlike zone electrophoresis, is not increasing over time. So the question is, can we combine both of them? Okay, so that we take benefit of high sensitivity and high resolution of separation. Okay, so this is something I've worked on extensively. So what we do is that, okay, and I'll try to show if I have simulations towards the later part of the day. So first we take a sample, we do ITP. Okay, okay, so what we have done is the initial concentration we have increased. Then what we do is we disrupt ITP. How do we disrupt ITP? We can disrupt ITP by disrupting the conditions which are causing ITP. So what we do is that, let's say we do focusing of ions, then we add the high mobility ions behind everything, okay, all the focus zones. So they will disrupt ITP and you will get zone electrophoresis. So here's an experiment which I had done long time back. So what I've done is I took a DNA ladder, okay, we focus the DNA ladder in ITP, okay, and you get a very high concentration of DNA starting from very low concentration of DNA. In that case, the concentration of DNA was, similar to what you will get from a single cell, okay. Then we disrupt ITP and you will start seeing various zones, the resolution increases. So the ITP step helps you increase the sensitivity, the zone electrophoresis step helps you increase the resolution. And recall, if you have a complicated device, okay, uh, a lab on a chip system where you want to do some sample extraction, you want to take sample around some turns and all, then you can use ITP, and once you are at the final stage, then you can disrupt ITP and then you can have separation. So that's one use of ITP. So with compared with microchip electrophoresis, which has extremely high separation resolution, ITP is not as such used for separation. Okay, you can use for separation, but if you have an option, zone electrophoresis is going to give you much higher resolution, but as a pre-concentration step, it really helps you improve the detection sensitivity. Okay, and although initially ITP was used for electrophoresis, then people found some innovative ways of using ITP for other purposes as well. Okay, the idea is that you can increase the concentration locally, so we can use it for other things. So one thing is to enhance some reactions. Okay, so let me give you one example, which is not about separation of ions. It's more about having reactions and having fast reactions and better detection. So let's say that you have a DNA strand, okay, and you want to do sequence specific DNA detection. So let's say a DNA strand has a particular sequence, right, and you want to see whether my sample has that particular DNA strand or not. Okay, for example, this kind of things you can DNA or RNA. For let's say for urinary tract infection, okay, you can take the sample, okay, do the cell lysis, okay, and then you will get RNA, for example, okay, and then you add a molecule, okay, which is called molecular beacon. Okay, essentially it is a molecule which binds to one particular strand, one particular sequence of DNA and emits fluorescence. Okay, so the idea is that if it finds that particular sequence, it emits fluorescence. If not, it will not. Okay, but you see that you need a hybridization reaction between your target and your probe. Okay, and typically if you do it in, let's say, a 96 well plate, okay, it can take very long time to detect reasonable concentrations of the nucleic acid. It can take a day, for example, for 10 picomolar target. So what we did was that, okay, we took both of these targets and probe, okay, we focus them in DNA. They have similar mobility, so they form zones which are overlapping. Okay, but imagine that for a reaction, okay, a reaction where you can increase the concentration of the probe and the target, because it's a second order follows second order reaction kinetics. Okay, so if you increase the concentration, let's say even tenfold of the reactants, two reactants, then your reaction rate increases by a factor of 100. Okay, 10, 10, 100. Okay, so if you can easily, we can pre-concentrate samples 100-fold or million-fold, okay, or 10,000 fold, then the reaction becomes very fast. Okay, so what reaction on normally takes a day, we can do it in seconds. Okay, that is the benefit of pre-concentrating. Again, keeping in mind, we are not replicating, we are not producing new DNA. All we are doing is we are confining them in a narrow zone. Okay, and all this is possible because we are using discontinuous electrolytes. Okay, we are using the self-sharpening physics of ITP, self-sharpening gradients in ITP, so that we can counter diffusion, because if the zones were to diffuse, then the concentration will go down. So with this introductory lecture, I'll Okay, I'll stop here. So what we have shown is that in ITP you can get self-sharpening concentration gradients, okay, which you can think of as shock waves, which are sharp waves which have a self correcting mechanism, self-sharpening mechanism, that they remain sharp as long as you apply electric field. We've seen how we can do basic ITP experiments, how we can choose electrolyte chemistry, okay, to choose ions, to make the assay with high mobility leading ions and low mobility trailing ions. Uh, Quickly, we've also seen how we can increase the detection sensitivity of ITP, okay, and how we can in ITP and zone electrophoresis to get best of both worlds, get highest sensitivity and the high resolution of zone electrophoresis. And lastly, I've also shown, uses of ITP for some other purposes, for enhancing hybridization reactions. But there are various other uses of ITP now. Okay, what people do is another application of ITP is sample purification. So what you do is that in ITP only those ions will focus whose mobilities are sandwiched between mobility of leading and trailing ions. So if you have, let's say, a cell lysate and you want to preferentially extract DNA, then what you can do is you can take leading ion and trailing ion such that only DNA or a particular size of DNA has mobility between the leading and the trailing ions. So when you do ITP, you will get focusing only of those DNA strands. Okay. For that, you need to choose the leading and the trailing electrolytes carefully. So that's about ITP. So remaining part of my lectures will be on how we can do simulations. So maybe that we can do after lunch. I don't know if you have access to computers, but if you can have computers, you can work with me also during the next lectures to do some simulations yourself, because we have very simple tools on internet. You can use those tools to simulate all of these processes that I have discussed. So with this, I'll stop. I'll be happy to take any questions.
Thank you,
Thank
Doctor, for nice lectures. And those who have a laptop with them, they can bring their laptop and use the simulation tools. And it will be very interesting for you to learn how to calculate the mobile speed and flow of the ions. Right? So we will meet exactly at 2 p.m.
बुखार मैंने आपको रात को बोला तो था कि दवाई करो बेटे आपने फीवर की दवाई ली आपने टेस्ट करके देखो आपको बोला था बेटे कोई बात नहीं तो दिन कोई प्रॉब्लम नहीं टेंशन मत लो मैं लग रहा हूँ टेंशन ले रही चीज़ पे और तो यहाँ पे भी ना वायरल हो रहा है कहते कि 3-4 जगह पर ना मौसम चेंज हो रहा है हाँ ठीक है तो मेरा शूट
मैं एमी वेट कर रहा okay let's start the next lecture. So this is modeling and simulations of electrophoresis. So this is like this lecture is in two parts. The first part is okay. So ठीक है? Okay. So now we'll start looking at modeling and simulations of electrophoresis. This is a two-part lecture. In the first part, we'll look at how to mathematically model the, in general, electrophoresis techniques. Okay, and you'll see that there is a common mathematical model for all electrophoresis techniques, which describes the motion of ions moving under applied electric field. And then what you will see is that various electrophoresis techniques like zone electrophoresis, field amplified sample stacking, ITP, are just different initial conditions or different setups of the initial conditions and the boundary conditions using the same mathematical model. Okay, so maybe this part you might not those who are not familiar with differential equations will have some difficulty. Just try to appreciate what are the various features in the mathematical model. In the second part of the lecture, if you have access to internet, we'll try to do hands-on, so that by working on computer you can make mistakes, try to do something which is not expected and see what are the outcomes. And that way I think what you can do is you can run a virtual experiment on your web browser using a tool that I helped develop, and with that you without even doing experiment you can actually learn various techniques yourself. So that would be more interesting, but let's just try to understand how those tools have been developed first, and then we'll see how we can use them. Okay, so please bear with me for the first part if you are not familiar with mathematical stuff, but it's essential if we have to describe simulations. So in the morning lecture I have discussed about zone electrophoresis, Okay, I'm just doing a quick recap because we are going to simulate this process in the later part of the lecture. So in zone electrophoresis, as you recall, we have a uniform background electrolyte concentration, a high, relatively high concentration of background electrolyte, and the samples are injected at the inlet, and we apply electric field. And when we do so, we see that these ions will get separated and the peaks will get diffused over time, and the separation distance will increase over time. That is what we've seen in the first lecture in the morning today, and how we have implemented in microchip electrophoresis is using this cross chip geometry. That is also we have discussed, but for our simulations we are not going to simulate the whole cross chip geometry. We are just going to do one dimensional simulation because that's easier to do. So we'll just look at this kind of a process in one dimension and we can see the simulation. Okay, we can simulate this process. So the idea of doing these simulations is that in advance, if you actually use the parameters that will be used in the experiment, you can get a sense of what will be the peak heights, what will be the resolution of separation, whether the two peaks are separated or not. And this we can try and to simulate in our experiment. Another thing that we discussed in our previous lectures was field amplified sample stacking. I said that if you have a gradient in the concentration of the background electrolyte, you can stack samples. So we can try to do simulations of this process as well. So you will appreciate how starting from a low concentration sample, your concentration can increase if you have differential electromigration velocity. Essentially, in the high conductivity region, the velocity is going to be low. In the low conductivity region, the velocity is going to be high. So the ions will get accumulated at this interface. So this is also something we'll try to simulate. Then we have discussed about ITP. This is a very complicated process to think about, and to design you have to judiciously choose the electrolytes, because in zone electrophoresis the choice of electrolytes is not so difficult, but here the process is very non-linear in ITP, and the choice of Le ion, Te ion, the counter ion, and depending upon the samples that you have is very challenging, and that is where simulations really help. Okay, so my whole PhD was on ITP and coupling ITP with zone electrophoresis. Actually, I spent a lot of time making these simulation tools, and most of the time, we could really simulate various electrolyte chemistries on computer, and so that when you go to the lab and do, after less amount of trials, you can actually get things working. Otherwise, designing ITP experiment is challenging, and it needs a lot of experience. But if you have simulations, you can gain that experience through simulations rather than spending time and spending resources in the lab, in a wet lab. So why do we need simulations? You all so these are the things related to ITP that we have seen in the morning. But why do we need simulations? So as you all appreciate, okay, many of you are not familiar with these things, how to do the experiment in practice, how to do electrophoresis in practice. Some of you might not even have access to the equipment, but you can still optimize the processes, how I can choose the process parameters to get improved sensitivity, improved resolution, and all of that practice you can do on the computer, because the models that we have now, the computer models and the simulation tools, they are fairly good representative of the reality. So I'll show you the experiments that we have done and the simulations that we do. They are in pretty good agreement. So all you can do is you can use simulation tools and make an optimal process, and then you start doing the experiments. Okay, and one of the challenge you will see is in designing LENTE for ITP. Okay, another thing is that we can also work on developing new electrophoresis processes, very complicated electrophoresis processes like bidirectional ITP. So I worked on this for some time, where you have some ITP fronts, anionic ITP fronts moving in one direction, cationic ITP fronts moving in other direction, all together in a single channel. That's very hard to think of, but you can do simulations and then make sense of it. Okay. Another point is that, see, when you do an experiment in a microfluidic device, okay, while doing the experiment, you can measure only the things that your detector gives you. You might get a fluorescence signal, you might get conductivity signal, but simulations will also give you the spatial and temporal variation of various parameters, like what was the pH at what location, what is the conductivity, how does the conductivity vary with the distance, all these things which you cannot measure using experiments, you can simulate. Okay, so that's the benefit. And of course teaching. Okay, I've tried to show you already some simulations in the previous lectures, and they actually help us understand how spatiotemporal variations in properties like conductivity, concentration, pH take place in electrophoresis processes. Okay, so now we are going to develop the model for simulating electrophoresis. Okay, some of you might find it a bit challenging, but let's just look at overall, processes that go into overall, like mathematical terms that go into the modeling, because really we have to solve differential equations to be able to model these processes. So what we'll do is we'll start with a simpler version first. We assume that the ions that I have in the solution are fully ionized. There is no association dissociation reactions. So you have strong acids and you have strong bases. So you might have, let's say, sodium chloride, potassium chloride, okay, calcium chloride, magnesium ions. All of these are, you can consider them to be fully ionized. So you don't have sodium in non-ionized state. It is mostly ionized state. You don't have chloride in aqueous solution in non-ionized state. It's not in HCl form, it's in Cl negative form. So that is what we assume. Because if we assume this, then we can assume that the electrophoretic mobilities are constants. Okay, so let's see. So what we do is, essentially the governing equations that we are going to solve are equations for mass balance. Okay, these are just conservation equations for mass balance. Okay, that's how we describe. So the equations go like this. Okay, if you consider a small control volume, a small space in your liquid, okay, small virtual region in the liquid, okay, think like, maybe you are more accustomed to some reactors and all. So imagine that I consider tiny volume of liquid, okay, in the microchannel. The rate of change of concentration of some species within that tiny volume will depend upon what is coming in and what is going out. Okay, so how can ions get in and how can ions get out? What are the various physical processes by which ions can get into this volume and get out of the volume? Okay, what are the processes? One is that liquid will flow. Okay, the ion is carried by the flow of the bulk liquid. Okay, that is called convection. So it is velocity of the fluid times the concentration. Okay, that is the mass flux that is coming in. Okay, then you have electromigration. Okay, let's say there is no flow of liquid, but the ions themselves are moving under the effect of electric field. So with what speed are they coming? Mobility times electric field, and how much amount of ions, what is the mass flux of ions per unit cross section? Okay, that is mobility times electric field is the velocity times the concentration. Okay, this is the amount of ions that are being that are crossing a particular cross sectional area. Okay, and then what we have is diffusion. Okay, because of diffusion, also you will have flux in and out of the system, and diffusion, the flux due to diffusion is modeled as minus diffusivity times the gradient in concentration. So why is this minus sign in diffusion? Minus sign is because mass will flow from high concentration to low concentration, and there is this derivative term. So you put all of this together, you get a transport equation. This is a partial differential equation, okay, and we need to solve this equation for all the ions that I have in the system. Okay, so I may have, okay, an electrophoretic system which has 10 different species of ions. Okay, maybe sodium, calcium, chloride, sulfate, magnesium, so many ions. So each of these species will be described by a different differential equation, because those species will have different mobility and different diffusivity. Okay, now we also have one more parameter over here, one more variable over here, that is the electric field. Okay, so electric field also depends upon, what does electric field depend upon? I have a capillary, I am applying voltage. What will electric field depend upon? It will depend upon, it will depend upon the voltage, it will depend upon the length, but it is also going to depend upon what is inside the capillary. Okay, is the solution more conductive? Is it less conductive? Okay, because if the conductivity is uniform, then electric field is just voltage divided by length. But imagine that one part has higher conductivity, other part has lower conductivity. It is like in high school physics. Okay, there is one resistor connecting between this region, and there is another resistor connecting between this region. So you can have different electric fields in different parts of the channel. Okay, so the equation for electric field actually can be derived using the electroneutrality assumption. The electroneutrality assumption means at every location in the capillary you have same number of positive ions as same number of negative ions, or you can say the net charge should be 0. Okay, because you can't say same number of positive and negative ions, because some ions carry more charge, some ions carry less charge depending upon the valency. Okay, so but net charge should be the same. So based on that, you can actually derive the Ohm's law. This is the Ohm's law, which says electric field is equal to the current density divided by the local conductivity of the solution. Okay, so when I say local conductivity, the conductivity is itself a function of concentration. So conductivity depends upon the concentration of the solution. And here we also have a contribution due to diffusion. Okay, different ions diffuse at different rates, so they can also produce a current, okay, a diffusion current. But this term is not so important as much as this conduction current. Okay, so this is my mathematical model, okay, for fully ionized species. But the species that we are going to look at, the chemical species that we will be working with, are weak acids. They are not fully ionized species. So what we have to see is that we have to ensure that the dependence of the mobility on the ionization of the species is taken into account. That means depending upon the pH of the solution, how much fraction of particular species is in ionized state and how much is it in non-ionized state, it will dictate whether the mobility is high or low. Okay. So for example, what we can do is, typically, let's say we have a mixture of sodium hydroxide, acetic acid and phosphoric acid. Okay, and we want to simulate this kind of a mixture. So what are the various acid-base equilibrium reactions going on? So there are a lot of reactions that are going on, and you know that, and in chemistry we know that I give you a particular composition, you mix it, you can always calculate the pH, isn't it? Okay, you can always make buffers, you know how to calculate the pH of the buffers. The same thing we have to do. So we assume that the acid-base equilibrium reactions, they occur instantaneously. They occur at much faster time scales than the time scale at which ions move. So ions move relatively slow compared to the rate at which acid-base equilibrium is established. So we always assume that equilibrium is already there. Always locally chemical equilibrium is already established. Acid-base equilibrium is already established. So using this, okay, the mathematics of acid-base equilibrium reactions, we can actually calculate what is the pH of the solution. Once we have the pH of the solution, we know that we can actually work out what is the ionization fraction of various species. Okay. So let's see. Okay, so it's just generalization of what you already know for acid-base equilibrium. Okay, do you know, right? If you mix acid and base, you can predict the pH. Huh? Which equation is that? What do you name? Hasselbalch. Okay, so essentially this is just generalization of that Hasselbalch for n number of species. Okay, that's all. Okay, it's just mathematical representation of what you do. Okay, for simple buffers, only thing here is that we have n number of species because in a capillary, in a microchannel at a particular location, okay, in my simulation I may have hundreds of species. Okay, so we just need a model to predict that if you have so many acids and bases, okay, what is the pH. Okay, and once you get the pH, you can tell what is, let's say in this case acetic acid, what is the fraction of acetic acid in ionized state, what is the fraction in non-ionized state. Okay. Now, in this example, we have two types of species. One on the top, sodium and acetic acid are univalent species. They can dissociate into, okay, they have only one ionization state, okay, or dissociation state. But here I have, what is this? Phosphoric acid. It has 3 ionization states. Okay, so what we actually solve for is the total concentrations. We solve for the total concentrations, that is, the total concentration means concentration of a particular species in ionized state plus non-ionized state. So for one species family, we write one equation. Okay, and if we do so and we work out the math for this, so essentially by solving these set of equations, the output is the pH of the solution, the local pH of the solution. The pH of the solution in capillary electrophoresis is going to change with location and with time. So at every time and at every location, you have to calculate the pH. Okay, and once you calculate the pH, you will have to calculate the fraction. Okay, let's say this is the ionization fraction of species X in Z ionization state. For example, phosphoric acid in -2 ionization state, this formula can give you. Okay, so this we have to solve at every time. Okay, every time step at every location. Now we can generalize our mathematical model. Okay, we have similar equations like we have for for fully ionized species. The only difference now is that if you look at this equation, it has this advection term due to motion of the bulk fluid. This is the electromigration term due to the motion of ions under the effect of electric field. This is the diffusion term because of diffusion. The only difference between fully ionized species and weakly ionized species is that this mobility is not a constant. This mobility is a function of pH. Okay, essentially, let's say for univalent acid, okay, this mobility is the mobility of the anion multiplied by what fraction of the acid is in the anionic state. Okay, and which is given by this term. Okay, you see the non-linearity over here. Okay, it's highly non-linear problem because of two reasons. So for at any location you have some concentration of various species. Okay, those concentration of species will dictate the local conductivity of the solution. The local conductivity will dictate the electric field. Okay, the electric field will govern the speed of the ions. Okay, and the speed of the ions is going to change the concentration. That is one complication. Another complication is the local composition of the ions is going to change the pH. The pH is going to change the mobility is going to change the concentration. Okay, so that is why doing nonlinear electrophoresis in presence with weak electrolytes, okay, is a highly nonlinear problem. So sometimes it's very difficult to predict what's going to happen in the simulation. Okay, only through experience and running simulations you will be able to understand why pH is increasing in a particular location, why electric field is increasing in another location. So what we do is that we solve these equations. Okay, we can also derive approximate equations for channels with variable cross sectional area if we work with average concentrations. Concentrations that are averaged over one cross sectional area. But for this lecture we'll just assume that the channels are straight. Okay, these are straight channels. Let's say we say there's no variation in the cross section, and therefore these equations will apply for single dimensions. Okay, so we'll just assume area is constant. Okay, we'll not do variable area. So the equations will simplify to this. Okay, one dimensional. We have one dimensional problem. Okay, so concentrations are functions of the spatial location x and time. Okay, so they can vary in space, they can vary in time. Okay, and these coupled equations we have to solve together. Okay, so depending upon the composition of the electrolytes, sometimes you may have just 3 species in electrolyte, sometimes you have 20 species. For other electrophoretic processes, there's one process called isoelectric focusing, which is used for protein purification. Okay, you may have 300, 400, thousands of species because it has some species called ampholites. So there you have to solve thousands of equations together, and all of those equations are coupled with each other because each concentration contributes to pH, each concentration of each species contributes to the conductivity. Okay, and conductivity will dictate the speed of the ion. So it's a challenging equation, challenging system of equations, and it's not that like you already develop your mathematical or your simulation tool for 2 equations or 10 equations. We have to simulate for general number of equations. Okay, because when you tell these are the species that I have in my system, okay, then your numerical solver or your simulator has to work with those many number of equations. So very quick introduction to, or brief introduction to how we solve this. Okay, so these are partial differential equations. Okay, in space and time. We need to solve them, but computers cannot handle continuous variables, so we discretize the domain into finite number of grid points. You can't define concentrations at all the locations because computer has finite memory. Okay, so these are called nodes. Okay, I'm telling you this because we are going to use this in our simulation exercises. When we simulate this, you will have to choose the number of grid points. So if you have large number of grid points, okay, intuitively it is clear that you are more closer to the reality. If you have less grid points, you are having a poor approximation of the actual system. The next step is to approximate the derivatives. Okay, the spatial derivatives, del by del x. How do we approximate the derivatives? We use the approximation formulas, okay, the finite difference formulas for approximation. Okay, because we don't know the, see, if I know, let's say f of x is e to power minus x, then you can calculate the derivative. But we don't have analytical expressions. We just have values of these functions at discrete locations. And using those values, we need to find the derivatives. Okay, so there are various schemes. Okay, for an end user, what you need to know is the order of accuracy of scheme. Okay, so typically there's one scheme called upwind scheme or first order scheme, which is presented over there. So first order schemes are, okay, will give you stable simulations, but they are inaccurate. Okay, high order simulations will give you, in some cases, unstable simulations if your grid is not fine enough, but they are more accurate. Okay, so there's nothing like you can get a numerical method which is easy to solve and also accurate. Okay, there's always a trade-off. Okay, so there are various schemes. Okay, this scheme that I have presented is called finite difference method. Finite difference method for approximation of derivatives. Okay, so in mechanical engineering we work on simulating flows of fluids. Okay, it's called computational fluid dynamics, CFD. In CFD, we study all these methods, how to develop advanced methods for solving, which are more accurate and which are more robust. So there's another method called finite volume method, but as a user you don't really need to know what this method is, but it's something similar to finite difference method, and you can use this method, and we've used this method to develop our numerical code that I'll be showing. Okay, so that's one thing. Okay, now what we do is the spatial derivatives, now we approximate in terms of the function values at various grade points. Okay, so okay, these derivatives we can make an approximation in terms of the flux values at various grid points. So what we do is that we end up getting differential equations for concentrations at every grid point. We get coupled ordinary differential equations for every concentration of every species at every grid point. So let me give you an example. So if you have a domain of, let's say, this big capillary, you say that I want to approximate this in terms of 100 grid points. Okay, and there are 3 species. So at every grid point, you will have to solve for concentration of 3 species. So in all, you will have 3 ordinary differential equations at one grid point, and you have 100 grid points, so you have 300 ordinary differential equations. Okay, if you have 100 species, okay, or let's say 20 species and 1000 grid points, you're at every time step from going from, let's say, 1 second to 1 millisecond. Okay, you are solving 10 into 20 into 1000, whatever. So you'll get 20,000 equations together. Okay, which is actually not difficult on modern computers. So we have developed tools, okay, for the end user, which can be implemented even on a web browser. Okay, so there are known methods of time integration to solve ordinary differential equations. Those who are familiar will know, but essentially you can numerically solve at discrete time steps. So you can solve for small time intervals these equations. Okay, some tools will allow you to adapt the grid. Okay, so the idea is this. Okay, so in ITP, you know that we will have very sharp concentration gradient. Okay, to resolve a sharp concentration gradient, you need very fine grid spacing. The computational grid, the grid points should be very, very close by. So if we take very fine grid throughout the domain, then the number of grid points increases, the number of equations will increase. So what we do is that we have algorithm where these grids will move in the direction where you have sharp concentration gradients, where you don't need these grid points. Okay, you remove from there and you place them in location where they are concentration gradients. So you can make your simulation more efficient. Okay, and the speed can be increased. Okay, so this is just a very brief introduction to what goes on in developing these numerical simulators. Okay, as an end user, you just need to have some idea like which scheme should I use, which tool should I use. Okay, should I trust my simulations? When should I not trust my simulations? That is what you should understand. So fortunately, in electrophoresis community, the good thing is that all of the tools, in fact, most of the simulation tools are available to the public for free, and you can just use them on your personal computer. So here are some simulation tools. Okay, so I'll use one of them to demonstrate these simulations. So let's see. So Simul is developed by researchers in Czech Republic, and this was originally the only simulator available, and the new version is really good. It's very robust and it has a large database of chemical species you can use for testing, and the new interface that they have released with the version number 6 is really user friendly. You can use it if you want. All other three, fortunately, I have been involved in making all the three simulators. Okay, they solve similar equations, but they have different utility. So this simulator was developed at Stanford University. I was one of the contributors to this. So simulator works on MATLAB, and it has in terms of accuracy, it's very accurate. It has you have a choice of choosing the order of accuracy, because in Simul you don't have handle over what is the accuracy of the computational techniques that you use. In this you can get that, and it has adaptive grid refinement. Simul does not have. So here you can solve the same problem in lesser amount of time. Okay, so that's the benefit. Okay, this is another tool that we developed along with the team at Stanford University with Professor Juan Santiago. So the objective of this tool was not to be very accurate, but even like a beginner can actually quickly use it without installing the software or anything. So it is available on the web browser. So in today's lecture, because I find this tool very handy, okay, we can use this tool on our web browser to do the simulations. But one has to be careful about the accuracy, because it uses simpler, easier schemes, which may have lower accuracy, but qualitatively you will get the correct answer. Okay. Then we also worked on developing a very, very high accuracy solver. It's called pseudospectral Python code for electrophoresis. So pseudospectral method is the highest accuracy numerical scheme that you can develop. The need for this program came because many times I'll show you. So for example, you can use this Python code to run thousands of simulations, okay, and you can program it in this fashion. These are based on graphical user interface, so if you have to do 1,000 simulations, it's very difficult. You have to do it manually. So if you have a Python-based code where you can actually make the input files and you can run them in a batch, okay, you can do a large number of simulations very easily. So in the later second part of this lecture, I'll discuss this tool, and we'll try to do some simulation so that you will understand yourself, by making mistakes, what can go wrong in an electrophoresis experiment. But let's just compare these simulators. Okay, so Simul simulator is good, but its spatial discretization accuracy is only second order. Okay, the order of accuracy describes how well you can describe the derivatives or spatial derivatives using the approximate formulas. Okay, so second order is good. Okay, but sometimes you need very high order accuracy. So Espresso and Spice gives you the highest accuracy. This Cafes one, the web browser based, has reasonable accuracy, but not as good as all of them, because we have tried to make a scheme which is more robust to make it user friendly, so that you don't see your simulations blowing up. Okay, so it's a trade off between user convenience and accuracy. Most of these schemes use similar time integration schemes. Espresso and Spice also give option for adaptive grid, so you can use less number of grid points and simulate a more complicated problem. Espresso, we also integrated variable cross-sectional area feature. So for example, when you have ITP in a variable cross-sectional area channel, you can simulate in Espresso. And all of them have graphical user interface, except Spice one, which was not made for graphical user interface. So what I'll show you now is some test cases, and then our objective is to run some of these test cases, set up these test cases ourselves on our computer, and then try to run those, okay, in one of the simulators. So we'll use only Cafes because you will need MATLAB for this, Python for this. So it's better that we just use what is available on a web browser. And those who don't have a computer may also try it on mobile phone. You can still, I think you can run on a mobile phone also. Okay, but let's try to do, let's just look at the simulations. So this simulation is for capillary zone electrophoresis. I have quickly shown in the first lecture. So initially there were two overlapping zones and they are separating over time. Okay, so what you see is that these peaks are getting separated over time. Okay, but the background concentration is also changing, because here the concentration of species is, the zones is pretty high, relatively high, that it is changing the local electric field. So the background concentration is also changing. Okay, if the background concentration was not changing, then you will not get these triangle shaped zones. So here we have done simulations using various schemes. So some schemes which are inaccurate but robust will give you this kind of solid line, this black line, okay, where the solution does not capture the peak exactly. It will capture the location of the peak exactly, but the numerical method adds some additional diffusion to stabilize the simulation. Okay? And sometimes if your scheme is not correct, then you will see these oscillations. Okay, so in the simulator that I'm going to teach you, you will never get these oscillations because we already, artificially added some diffusion to suppress them. Now let's look at simulation of ITP. We saw this simulation of ITP earlier. Okay, we can try to set up another simulation like this. So this is leading electrolyte, trailing electrolyte, some sample ions which are separating over time. So what can you get out of this simulation? What should be the length of the channel so that my separation is complete? Okay, in what time I will be able to get the separation? These are the things you can simulate before even doing the experiment. And here's the same simulation just to show that various simulators give you similar answers. So we verified or benchmarked Espresso and Spice. So both of them give similar answers. So you can use any one of them. Okay. Now for ITP problem, this is a simulation of focusing of two analytes, aniline and pyridine, between sodium and an amino acid. So here you see that if you choose a less accurate numerical scheme like the upwind scheme, then this interface will not be sharp. Okay, just because less accurate schemes add more additional diffusion than what it is present in the simulation. Okay, so you will see more diffused interface, and this diffusion will increase if you have lesser number of grid points. So this is best learned through practice. So we'll try to experiment ourselves and try to see. Okay, so the point is that the zone boundary thickness, the thickness of the zone boundary will reduce with the number of grid points. If you use larger and larger number of grid points, your simulation becomes more and more accurate. Okay, but for some schemes using less number of grid points, you can get that much accuracy. But if you are not worried about accuracy, you are just worried about just qualitatively understanding, then it doesn't matter. You can use less number of grid points and have an approximate simulation. Okay, so now at the end of my capillary electrophoresis lecture, I had talked about sample stacking in zone electrophoresis. Okay, so let me see if I can stop this. Okay, let's look at this simulation again. So what I have done is, this is again zone electrophoresis, but I have created a gradient in the concentration of the background electrolyte. So essentially what you have is, if I can stop or start again. So you have high concentration background electrolyte, the sample is mixed in low concentration electrolyte. So when you apply electric field, you see that this concentration initially increases. Okay, the zone becomes narrow, the concentration increases, and then you start seeing these separations. Okay, so this is how sample stacking and zone electrophoresis can help you increase the sensitivity. So we can see it again. So in this plug you have small amount of samples. Now the concentration is initially increasing, and now once the stacking has taken place, now you get electrophoretic separation. So even though if you have low initial concentration, you can use this stacking process in the beginning for pre-concentration and then improve your sensitivity. Okay, so these simulators you can also validate, okay, with experiments. So for example, Espresso, we have done validation with experiments. So let me show you this case, okay, over here. So this was an ITP experiment where there were 3 species. Okay, we had fluorescein, we had another fluorescent dye called OGCA, and there is another species focused between these two, but it is not fluorescent, so it is not visible. So you see the match between experiment and simulation is excellent. Okay, this is experiment and this is simulation. Okay, similarly, this was another experiment where we did plateau mode ITP with non-focusing tracers. So we said this, we measured that LE zone was up till here, then we have some analyte focused between LE and TE, and that is what we have simulated. Okay. So the mobilities besides pH are also function of ionic strength. That's a secondary correction we make in the simulations, and how much sample is accumulated in experiments and simulations, they match pretty well with the simulations. So the goal is that now that we have validated our simulations, various people have done a lot of experiments. We've tried to validate our tools with those experiments, and the match is pretty good. Okay, so we can trust our simulators and now start building or trying to develop our experiments using simulators. Okay, so that is about these developing simulators using from first principles, using the mathematical tools. This is our recent work, just some idea that we thought about and we tried to implement. So what we did was that, see, for a person this work is specific for ITP only. So the idea is that, you know, for an end user, many times you don't even need to do the full simulation. All you need to know is if this is the LE, this is TE, will ITP work or not? That's all you are interested in. Okay, or you say this is the sample I want, will this ITP work or not? So what we did was this, okay, we used our SPICE simulator, okay, and we did 10,000 simulations for an ionic ITP, 10,000 simulations for cationic ITP. We got a very large database of simulations for a certain type of electrolytes only, univalent electrolytes, okay, these kind of electrolytes, where we varied mobilities between these values, you know, pK between these values, okay. So we took, you know, a large number of simulations, okay. Some of them showed ITP, some of them were not consistent with ITP focusing, but what we said was that we take large samples, you know, large number of parameters. We take, you know, large samples of parameter values, and we do simulations. We got large data set, okay, and it's a highly nonlinear problem. Then what we did was, it's these days very easy to train a neural network model, okay, for classification. So we said that what are the inputs to my model? Inputs are mobility and pKa. So I have LE, TE, and analyte. Each of them has a mobility and each of them has a pKa. So we feed this, okay, and we train the model based on large number of simulations, and we make only one prediction, whether you get ITP focusing or whether your experiment is going to fail, okay. And then we trained this model and made a small online tool, okay, it's called GIAN. All you have to do is, it will not give you spatio-temporal variation of the physical properties. All it will tell you is that if I choose an LE, if I choose a TE, I choose a background counter ion, and I choose an analyte and say predict, it will immediately give you an estimate whether your ITP is going to work or not. Okay, so for an end user, okay, it has an accuracy of 97%. Okay, so most of the time it's going to work. So end user sometimes doesn't even really need to look at the whole simulation, because doing these simulations is also, you know, setting up these simulations can also be challenging for some people. So those who are really into experiments and quickly want to know, okay, this chemistry, you can just put it in this tool. It's a web-based tool, and then it will predict, okay, for ITP this is going to work. So we can try these two tools in the next part of our lecture, where we'll do some hands-on work. Okay, so what I will suggest is okay, in the break, okay, I can give you the links to these tools. So let me see, try to open these links so that we can work on these links in the next lecture. So is there a way I can share the link with people? Let's see.
Yes, we are.
Or you can type this link if you want.
We have a WhatsApp group
You have a WhatsApp group?
of this.
So I can share it on the WhatsApp group.
Admin has to add you. Huh? Admin.
Who is the admin?
Sir is there. Vikas is admin. Vikas is admin. He's not there today? He's not here today?
You want group?
No sir, group is there. He just want to share the links in the group. For that admin has to add him, na?
Or you can try writing this. Okay.
Group link.
Wait, I will do something. I'll do something, don't worry. Let me fix it. नहीं मैं बता रहा हूँ आसान तरीके बता रहा हूँ I will give an easy. Okay, you can scan this code and see if you can open. Huh? No, you will get the link on the phone only. See if it is possible for you to. At least you will get the link. Okay, this site will take time because it runs on JavaScript. It will take a little time to load. So if it is, she has WhatsApp. It will take time, little bit time to load. Okay. Another, if you can send another one on WhatsApp. So this is the second one. So these are the two tools we will use. It will take a bit. Just wait for a bit to. Okay. So should we start with this or? Huh? Okay. Are you ready, guys? Huh? So we can work with the other one first. वो खुल जाएगा because the way it is written is that it's not running on a server, it's running on your own computer. So it's when you do these calculations, the calculations happen in the browser only, not you don't need internet after this. Okay. So it will take time to load. But if you have opened the other one, we can. this one is open for you? Okay, so let's try this one first. This is easier, right? But it's not going to give you much, okay? I mean, it'll just give you one output. So let's see. So, okay. So thing is that let's say we want to simulate. Okay, so this part of the lecture we'll start, doing hands-on work. Okay, there are no lecture slides for these in this lecture. So see, this is the neural network tool that we developed. All you have to do is that you have to give the choice. It a general. You tell whether what LTE background analyte you are choosing, and it's going to predict whether IP focusing will take place or not. That's all. Okay, and it has been trained using large number of simulations. Okay, and some of the simulations are validated with the experiment. So we hope that whatever this is predicting is correct. Okay, so what we have to do to use this simulator is that first you choose what type of ITP are you using. Are you using anionic ITP or cationic ITP? Okay, anionic ITP is to focus and separate anions, negatively charged ions. Cationic is for concentration ratio is the initial composition of the leading electrolyte. So typically we say that for a buffered electrolytes, you take let's say around counter to leading to be 2. Okay, so we will not change this. Right? So now let's try to design an ITP experiment. So let's say if you choose an anionic ITP, you will be shown only acids over here. Okay, you can also put your own values if you want, but let's say I choose. So I choose hydrochloric acid. Okay, so hydrochloric acid will give chloride ion as the leading electrolyte. Okay. Okay, you can choose hydrochloric acid, for example. Okay, then background electrolyte, you can choose, let's say, tris. Okay, so whenever you choose from the database, it will update the mobility and the pK over here.
Here it is already coming next.
Yeah, that is because you're using for the first time of school. You can just do next and finish it off. It's just help.
Okay.
Okay, TE and okay, so see this. I have used. You can have a look and then maybe try later. Okay. So in leading electrolyte, I have used the chloride ion, which is an ion of hydrochloric acid. Background, I have chosen tris. Okay. Trailing electrolyte, I have used heaps. Okay. So what you see is, first look at this. Mobility of heaps is anyway low, but the pK is also high. That means it's a weak acid. Okay, with a low mobility. So certainly it is slower than the chloride ion. The mobility is lesser than chloride ion. Okay, but I have an analyte MOPS. Okay, so MOPS has higher mobility in terms of magnitude, and it also actually has it's a slightly stronger acid than heaps. Okay, so that means this analyte must focus between this Le and Te. Okay, and from experience I know. Okay, and you can also judge. But what you can do is you can hit predict and it predicts. Okay, it not only predicts, it also gives some number. You can interpret it as a probability, but it's not exactly probability, but it's, you can think that the code is 99% sure that this is going to work. Okay, because again this is based on a large data set, limited data set, so we don't want to give, you know, predictions like this is going to work, this is not going to work. Okay, there are some cases which are borderline where the model is confused. It will say that okay, the accuracy, this probability of ITP condition satisfied will be lower. Okay, but here in this case it is fine. Okay.
Why we have chosen that concentration ratio
Huh.
2?
Typically you choose it to 2 because when we, as I said, when you make the electrolytes for ITP and you want to have certain good buffering, what you do is that you take one part of strong acid and add 2 parts of weak base.
Okay.
So that gives you a good buffering condition, that's all. Yes.
Does it only do the simulations at the pH of the pK, or is there a way that you can adjust the pH? Like heat is not
Yeah.
good
So
for-
if you change this,
Yeah?
then the pH is not pK, right?
Okay.
Yeah. So you have a handle over here, so you can modify this over here. Yeah. So you can
Okay, so
change.
you did that's what you use to titrate your buffer.
Yeah. So this will help you titrate and control the pH of the LE, and then it will do. But for beginners, we always recommend that you use this ratio to be 2 because then pH is, you know, that pH is equal to the pK. Yeah, that's the only reason. But if you want to do titration, you can change this value. It the model is trained for the range 1.5 to 3. Okay, which is typically what you use. Okay, now let's check. Okay, so now what I'll do is I'll take MOPS as my LE and change analyte to hydrochloric acid. Okay, so now LE is still faster than TE, but my analyte is faster than LE. So let's see. Okay, so it gives you this condition that it's very sure that it's not going to work. Okay, but you can actually simulate more complicated cases also over here, which might not be so trivial. Okay, this is a trivial example, but the benefit is that, you know, I found it useful because many times you are in the middle of the experiment, you think, okay, let me use this. So then you don't want to set up simulations. You just open it on phone or computer, quickly see, okay, will this work? Okay, most likely it's going to work, so you can try it out. Okay, so for quick like initial screening of various electrolyte systems, this is very good because you don't have to set up detailed simulations. But if you really want to understand how, you know, simulation is progressing, how focusing and separation is progressing, then you actually really have to do the full simulations, which is also not hard to do. Okay, are you able to understand? I'll be available after the class also, so if there's any help required, I'll help you after the class. So yeah.
Now you've got all your databases. How far are you away where this says, no, this is not going to work, but maybe change your leading electrolytes to, well, not sure what you, with chloride, what you do, you change your leading electrolyte. But how big would the step be to say, no, this is not going to work, but your leading electrolyte?
Yeah. So actually,
So suggested
yeah.
alternatives.
So let's see. So let's fix our LE over here. Okay, LE and background is fixed. Let's just try to play with TE and analyte. This is predicting the whole experiment, whether analyte mobility is between LE mobility and TE mobility. Okay, so now if we just run this, obviously it's having issues because I've given the same analyte here. But let's see. Let's get it to the working point, because Um, okay, so it says uh, MOPS will get focused between heaps and hydrochloric acid. We are back to what we've seen earlier. Okay, now you can try to change the mobility value. Okay, so let's say that I'll just customize this. So I'll say pK 7.5. Okay, the only difference now is that the mobilities are different. So let's see if it predicts. Okay, so it's still predicting because analyte mobility is higher than the TE mobility. So we can start decreasing the TE mobility, the analyte mobility. Okay, so it is 25 and this is 23.5. So let's see, it is still predicting, but this red one is slightly increasing. It's getting a bit more confused. Okay, so we go to 24. Okay, this is slightly more confused. If we do 23, okay, so it's giving a wrong prediction, but this peak is also slightly bigger. Okay, because ideally now it's not able to recognize between 23 and 23.5. Okay, because it depends on the simulation data, whether that data was available in this range. Okay, so now there is some confusion. So the point is that once you start seeing confusion in the code, you have to verify with the exact simulator. So maybe in certain cases you saw, okay, there was prediction, but now 21 and 23.5, it is clearly able to differentiate. So as I said, this is not a accurate tool. Okay, this is a tool that if you have large number of choices, you can quickly screen so that now you can do a better simulation. Yeah, but it's handy because you can get some estimate. Okay, if this green and red peaks are really big, you are more or less sure that it is going to work.
Ideally, there should not be any red.
Ideally, it should not be there.
It should not be there.
Yeah.
Complete successful experiment.
Yeah. I've deliberately done a bad experiment here. Okay. So this is just for ITP. I mean, it's not for general purpose use. So let's see. So I hope this is open for you now, for everyone. Chaliye piche. For you. Okay. So now let's try to run this. Okay. So tell me, like, what do you want to simulate? If you have some choice, we can try to set up that. Okay. So what you have to do in this is that first you need to add all the species that are present. So let's just simulate the same. Let's just, I think this is not limited to ITP. We can simulate whatever you want. Okay, but let's just simulate the ITP problem, that the buffer that we have already set up. Okay, so what I'll do is go to search. Okay, I'll just add all the species. So you do add hydrochloric acid, and you can add it to your model. Okay. So you search hydrochloric acid in the database and click add. Okay, let me show you for another one. Okay, in search, let's search HEPES, heaps, and then hit add. Okay, are you able to do it, ma'am?
Yes.
Okay, then another one is, let's say, tris, TRIS. Okay, there's bistris and tris. I'll add tris. Okay. And then I will add MOPS, MOPS. Okay, so what you can do is, in the database, just search these 4 names and just add them to your model. Okay. Are you able to do it? Okay. Okay. So now what you can do is, actually if you scroll down you will see concentrations, but then we have not defined the we have not defined the profiles as yet. Okay. So what we'll do is, now we have to tell where is hydrochloric acid, where is heaps, where is trace. Okay. All we have just told the model is that these are the species that we have. So what I do is that hydrochloric acid we want to add on the right hand side of the computational domain. So I'll say right plateau. Okay, and I'll define its concentration. So let's say 100 millimolar. This is the injection length. Okay, we can use 20. Okay, so what do we need? Look at this. Okay, we need to define the concentration of the leading electrolyte, the initial concentration distribution of leading electrolyte. So I have concentration versus X. I want some LE like this. So I choose the option right plateau. So it makes a profile like this, but you need to tell at what point it is injected. So that is this X injection. You can just write 20 or 15, because I am simulating a domain of 40 millimeters length at 15 millimeter length from the left hand side. Okay, the LE zone has started. Okay, initially, and its concentration is 100. So you get initial profile something like this. Okay, it's 100 up till here, and then at 15 it is going to 0. Okay, so I suggest that you can use these values here, 100 and 15. Is that okay? Are you able to do it? Okay, so now what do we want? We want heaps as a TE, trailing electrolyte. So we want a zone on the left hand side. So we say left plateau. You can choose some value. You can take 10, let's say, millimolar, and you inject it at, you can even inject it at 15. Okay, so this is my LE. And this is my TE. Okay, is that fine? Okay, so let me, okay, trace is my counter ion. I'll just use uniform. I'm taking it to be 200 millimolar because I'm taking it to be twice that of hydrochloric acid. So this is my system. Actually, I can slightly increase the TE concentration so that it is visible. So maybe 30 I can do. Okay. So this is my initial condition. Please have a look. So this is hydrochloric acid on the right hand side. Okay. This is heaps on the left hand side, and trace is my background counter ion on the top. Are you able to get? Okay. So now what we need to do is we need to add our analyte. Okay. So analyte we'll add as a peak at, let's see, Okay, so what I have done is for peaks in this code you have to define as the location where the peak is initially. Okay, what is the amount of sample that is injected in these units? So just put 40, 15, and what is the width, injection width of the peak? Okay, so what you will get is this is the peak that you will get, this red colored peak over here of the sample, and this is the initial condition. Okay. Are you in the back? Are you able to get up till this point? Okay, try to use these parameters. Okay, see if you have these parameters. It is just like a graphical way to define the initial conditions. That's all. Yeah.
How we have divided the length of various.
Yeah. So that is, I'm just giving an example. In an actual simulation, actual experiment, you have to see from where you are starting your where in the channel these samples are injected. Okay. So think of this as a capillary which is 40 millimeters long, and imagine that, and initially you had LE up till here and TE up till here. Okay. Yeah, that's an initial condition. Okay, and the samples were initially placed in between LE and TE. That's what we are just imagining. Okay, so another thing that is that we need to choose how long the simulation has to run. This is the physical time, like the experiment will run for 50 seconds, not on the computer, in reality. Okay, the number of grid points, you can just take 1000 grid points, and the current. Okay, current and the cross section area. So you just use default values, whatever these are, but make sure that the current is negative. Okay, so let me see if this runs on my computer. So yeah, so if I hit start, you see that the initial sample concentration, it is increasing. Okay, so you can predict the dynamics of ITP just on your computer. It's very user friendly way. You know, I did discuss the equations and all those things, but for an end user doesn't really need to know what is going into it. But you know that, you know, if you know the equations, then you will know the limitations of the tool, right? Somebody will say I can simulate DNA and all these things, but the models for mobility are that we are just taking weak electrolyte. Okay, there's no gel and all those things involved. Okay, are you able to get this at the back? So now what we can do is we can, we don't set up the simulation completely, in one go. So we can just try to now complicate things. Okay, we can add more analytes. Okay, so let me add more analytes. So let's see. Okay, we can try adding something called mess. Okay, and then add it in a different amount at the same location, maybe different width. Okay, so now I have two analytes. Okay, as you see, they have different mobility and different pKa. Okay. Okay, so you will get an initial condition which looks something like this. Okay, so you can use these parameters. Okay, so now are you able to do it, ma'am? So if you now hit start, okay, what you see is a very complicated process, but initially the two analytes are mixed with each other. Okay, not only their concentration is increasing, their zones are also separating, and eventually you will see two purified zones. You should see. Okay, another thing that you see is is that initial TE concentration was this, it has increased to this value. Okay, as I said, the TE concentration will adapt to a value which is proportional to the Le concentration. The analytes are slowly getting purified into two distinct zones. Okay. But what you see over here is that the red analyte, that is MOPS, is not in sufficient quantity to form a plateau. Okay, it still looks like a peak. So what I suggest is you go back here and maybe increase the initial amount of MOPS. So you can take 150, let's say. So that you have an initial condition which looks like this. And now if you run this code, okay, you should see two, nice purified plateau zones. Okay. Now, while the simulation is running, okay, we can see that the code also predicts what is the local electric field and the pH of the solution. Okay. So in brown color, it is predicting what is the pH of the various zones. Okay. You don't want, you can't predict this pH in advance. Okay, because it's a very dynamic process. Okay, so now you see you have two zones. They are trying to separate, but separation is not complete. Okay, it is going to take some time. So in an actual experiment, we need to know how much time we should wait or how long the channel should be so that the separation is complete. All of these things we can design using simulation. Okay, so slowly you are seeing that you are going towards two purified zones, and you can also predict the pH. Okay. Okay, so now we see that the simulation is complete. Okay, the focusing is complete. Okay, you have attained steady focusing of these analytes. Okay. Okay, and they also leave the domain if you let it go, simulation for longer time. Is that okay? So this is how you can set up ITP simulations, but in the same code you can simulate whatever you want. Okay, there is no limit to what you can do because it's a general model. You can simulate whatever you want. Okay, so what we can do is we can try to simulate. What should we simulate? Capillary zone electrophoresis is what we can try to simulate, and that simulation is easier. Okay, so let's say we want to now separate these two analytes, the same analytes using zone electrophoresis, but now we don't need a TE. Okay, so we can just get rid of this. Okay, we can get rid of heaps. I need a uniform concentration of hydrochloric acid to make the background electrolyte. So my background electrolyte should look like this. It has 100 millimolar hydrochloric acid, 200 millimolar tris. Okay, I have deleted heaps. Okay. And maybe for larger length, you can start injecting this at earlier, okay, at the inlet. Okay, so we are trying to just have a look here. Okay, we are trying to set up initial conditions like this, where we have uniform background electrolyte consisting of 200 millimolar trace, 100 millimolar hydrochloric acid, and I have two analytes which are initially mixed. So these are overlapping peaks at x equals to 5. So this initial condition is what we are trying to use. Yes, just try to use these values. Okay. So HCl and trace are uniform, others are peaks injected at x equals to 5, and for our calculations we can just use these values. Okay. Are you able to set up? So if you do it correctly, you should get this. Okay. Okay. So in this case, actually, you see the initial analyte concentration is pretty high. So you might see significant electromigration dispersion. Okay. So what's gone wrong? Oh, sorry. So, let's see.
We have to reduce it even.
No. Actually, this code can actually run for this. Let me run it. Actually, the graphical interface is made for is tuned for ITP. It is giving just some bug, okay, over here, but concentration gaps are present. Please bring injections closer. Let me set up. I have a input file which can probably fix it. Let's see. I think there is some bug. Okay, let's see. Let me. same data? Yeah, because I know the code is, I mean, the graphical interfaces is just checking if the initial condition is consistent with ITP, but actually you can run it for zone electrophoresis also. So that is what I'm trying. Okay, otherwise. So. So manually it's not allowing me. Let me see. Okay, I think maybe there's been change to some of this code afterwards. Okay, but let me show you something else actually. I think there is some limitation to what initial condition it is allowing, but actually I can show you with other tools that we have. So let's see. Okay, but that you might not be able. You can download it, but if you search, but spice. Okay, so I'll just show you another simulator. Okay, so this you can use. Okay, I'm not going to teach you this how to use this, but it's on my website. You can learn it. So for zone electrophoresis, okay, the same simulation we are just trying to show you. So okay, this one is very fast. Okay, because it's not on browser. So we had initially 2 zones. Okay, which were overlapping, and they have separated into distinct zones. Okay, so this is the spice code that I'm using. So it's pretty fast in that way. Okay, and this can also do ITP. Okay, this is for the 4 analytes ITP separation. So you can see. Okay, this code is much more accurate, but it's a bit difficult to use. Okay, for beginners. I had an input file for zone electrophoresis. I wanted to see if it could work, but somehow I'm having difficulties in uploading it.
Right now it is only working for ITP.
Yeah, there is a way to make it work for others also, but I'm trying to do it. Actually, I had saved input file, but maybe the version of this code has changed and now it is not taking that. Yeah, there is some change to this code. I'm sorry, so it's not allowing us. Let's see if it loads. Maybe we can work. Okay, so we can try this. And now let me add. Let me just try this. Yeah, this works. I mean, it's not the best way to do it, but it works. Okay, so let me just show you. Okay, so actually there are multiple profiles over here. Okay, but what I've done is that I have added hydrochloric acid on the right hand side, hydrochloric acid on the left hand side, trace on the right hand side, trace on the left hand side, and the samples in between. Okay, so this is the initial condition I have, but this red and blue are actually the same species. Just because I've added them separately, it looks like this. But now if we try to run the simulation, okay, you can try looking at these two peaks over here. Okay, so they are going to separate over time and also get distorted over time. Okay, so there is like severe electromigration dispersion over here. Okay, and if instead we have low concentrations, okay, then this electromigration dispersion will not be there. Okay, let's see. So I can zoom in. Okay, so now these two peaks are getting separated. Oh, the simulation ran for 500 seconds. Okay, so I've just zoomed in and run the simulation for longer time. So these were the two peaks initially that were overlapping, and now they're separating into distinct zones. Okay, so now the point to note over here is that while these zones are moving, let's track the electric field. Okay, so what you see over here is that these zones are actually affecting the local electric field also, and that is the reason this zone dispersion is taking place. If the zone concentration were low, that the electric field is not modified, you will not get this dispersion. So what we can do is we can further try to reduce. So we have 10, and let's say we take width of 1. Maybe also reduce this. Okay, so now the dispersion has significantly reduced, if not completely eliminated. But typically what we do is that we have very low concentrations for the samples. So you need to have like 1:100 ratio of the concentrations, and then you will see that the electromigration dispersion is not significant. But now you can see the peaks are not so distorted as we had.
1:200 for some analyte
Background. Essentially, this presence of analyte should not modify the electric field significantly. If it affects, then that means that you'll get nonlinear effects. For example, if I do here 50 and 50, and I start the simulation. Okay, so now you see that one side has sharpened a lot, and there is significant zone dispersion. So that is what we need to avoid. Okay. So I think I've just given you one quick lecture on how we can use these tools for simulation. Okay, you can try out the other tools as well. Let's see where it is. Okay, all of these tools are available on internet. So you can download them, you can read the help, and you can try to run these codes as well. Okay.
The help documentation for all of them is really extensive.
Yeah, there's a lot of.
Lectures, I just give the students the manuals and tell them, come solve this problem by tomorrow. And then
Yeah, it's very easy, and the video. Some of them have video tutorials also. Okay. Okay, so we can stop this lecture here. Okay. We have one more lecture.
I'm happy to do the microfabrication for you. I put there microfabrication anyway.
Okay, so if we can skip, is it okay? No, let's see.
Hello. Today this one.
The schedule said it was another one on microfabrication, but I'm covering so much microfabrication.
Yeah, so maybe you can cover that, right? Yeah. So I don't know how. Let's see. Recent.
So you were returning to Delhi today?
No, I'm going to Chandigarh.
Because on Monday I talk about a whole range of microfabrication.
Yeah, then I think it's overlapping. So there was this 3 to 4 for device fabrication, but if it's possible, then we can skip.
Professor Malik is in charge.
Hello. 8 minutes 5 3 4 5 6.
login to the वो नहीं पता है.
5, 3, 4, 5, 6.
10, 5, 10.
I think that's your package.
That's my boss.
बस
That's the show and tell for Monday. Are we okay to conclude today? Is that start day, will set be another one of my preparation, I will easily cover that on Monday.
yes.
Okay, good. So, yeah, I also bought some microfluidic devices after the lecture. If you want to see, we can. But yeah. So, any questions? Maybe we can.
Please go and have a look at the devices, because I think you will have glass.
We have glass, PDMS, PMMA, everything.
But I've got some 3D printed and PDMS ones and TFT ones coming with no glass.
Yeah. These are standard off-the-shelf devices. This is made in glass. This is just 3D printed. This is not a big deal. So
It's my board now.
This is made with artificial.
The 3D printer.
3D printer. This one.
किस नंबर पे पेज है?
So that fine resolution you can print on silicon wafer.
So they're polymer threads and then
Yeah.
the cavity between are those. So you print
नंबर
the lines and then cast PDMS
Yeah,
over it and then
yeah.
it becomes yes.
How it's done?
So
Electricity.
it's a printing.
Okay.
So we print something, some features, and then we pour a polymer, heat it up,
Okay.
and then we bond it on the glass. This is probably for some other process. These are machines, lightly machines by CNC. So in glass, you can have a look.
This one
So this is glass. This is glass. Actually, if you look,
It becomes a lot more realistic up in your hands.
Yeah.
if you look in the light,
So
see, you will see a cross connecting from this reservoir to this.
It's plus 10.
ये क्या कह रहा है?
For some bigger devices and all, this will be good. You did some displacement.
I was about to say, is that lateral flow?
Yeah.
Lateral displacement.
Yeah.